So good morning, everybody. Thank you for joining us here for the 15th annual Fall Conference, Master Gardener Fall Conference. And then you start out with doing some thank yous. First one I need to do is for Ryan Haley. Is the organizer for the Fall Conference. She's done a tremendous amount of work getting our speakers and getting things lined up, getting the write-up, put in the seed, and so forth. A lot of things she's done, and she's going to continue with helping out here today. She's probably going to take the lead after I leave, after probably introducing Mark, our first speaker here earlier today. I'm probably going to duck out, and then Ryan is going to take over, and she'll be assisted by, of course, Sean and Linda and Renew. So they're going to help carry the rest of the day here, but and I need to thank our tech team. I need to thank our tech team for all the work they've done and assisting with all the conferences and all our monthly meetings. And they will be here to help you. And I think most of you, there may be one or two people in here, Anthony and Sue, but if you haven't done it, please rename yourself so we got a first and last name that's recognizable. We really appreciate that so we know who is here. So we're up to about 150 folks, and that's great. We're going to have our first speaker come around 9:30. I got a few more introduction announcements to do. So here in a few minutes, we are getting towards the end of the year. So you have not volunteered or you're short on your service hours. There are a few major events still coming, but after the end of October, it's really slim. So we got a few things. Of course, we have the Fall Festival, which is being organized by Taffy Turner and Mike Welsh. I don't know if they need more help. They may jump in or may send a text or something, but I think they're doing pretty good getting signups for that day. Even if they got things signed up, you're more than welcome to come and visit the Fall Festival as a participant. But that's this Saturday. Hopefully the weather will cooperate for us. So that's one thing. Remember, it's 20 hours for advanced master gardeners. We need 20 hours. And Taffy's saying in the chat box, they have a few vacancies left at the Fall Festival. So you may want to reach out to Taffy or Michael or look online and look for the sign up. Then I'm going to show you a little PowerPoint here. CEWA's coming, CEWA, Close Encounters with Agriculture. So if you haven't got your 20 hours as an advanced master gardener, there's going to be plenty of opportunity, I think, if you get you filled out. 40 hours, if you're from the new class and you haven't done any hours, it's entirely possible you can do the whole, catch up or get a lot of your hours if you're short by participating in CEWA. I think the signups is pretty good for the first couple of weeks, but it is like a 4-week event. So there's plenty of opportunity still out there. So let me just show you this little PowerPoint that I don't know, I created, and we'll see if I can share that over to you. Let me get this, share my screen over. There's one. I have to do it maybe one more time. There we go. Now it's cooking. So Sean will probably help me out, maybe pop the link in there, or maybe Linda. But if you haven't signed up, please sign up. There's still a number of opportunities, and this is a great event. It's one of our main events that we participate in and support. The University of Maryland Extension. I know Trigonian's been doing this for a number of years. I believe this is Doug's last year, but he said that several times before, I think, too. So, and then it may be, Chuck Schuster may be taking over. But so think about this. If you haven't, you're short on hours, or even if you have your hours, they could use the help. So wanted to mention that. The next one is I've been working with folks from the Montgomery County Public School System, and what we're trying to do is to promote students in the public school system who may be interested in the environment, in agriculture and horticulture. Harris works closely with the folks with the Montgomery County Department of Environment Protection. And what they're going to do is they're going to have an event on November 1st at Gaithersburg High School. It's rain or shine. And they need volunteers. And the main thing you're going to be doing is you're going to be planting You're going to be planting trees, I think, mostly. Most of these are going to be native trees. There may be some shrubs and things like that, and perennials also that might be coming possibly from the Pope Farm. I don't know, but I know they're working on getting some trees, and they're trying to do some work up there at Gaithersburg High School. So I think Sean is going to help me later on, and she's going to send out a registration link. But right now, I just have the point of contact up there. It's Harris Trobman. He's the organizer. Been working with him. He works for the facilities department with Montgomery County Public School System. So they're going to try to enhance their essentially their bioretention facility up there at Gaithersburg High School, and hope you can make it. And if you participate the entire day, it's 4.5 hours. So it's a good chunk. It's a good chunk. And if you want to help Harris and you want to get a little bit more involved in there and set up or clean up, talk to him. If maybe you can get some additional hours if you're short. So it's maybe one event where you can get a good bundle of your hours, and hopefully. So remember, December 31st, please enter those hours in. So the last thing I'm going to plug one of the classes that is yet to start at Montgomery College. It's the stormwater maintenance class. And the dates I had posted earlier may have been one of the dates, or one of the two of the dates may have been from last year's class, but the correct dates are up there. It's just three Thursdays. It's 3 all-day Thursdays, and you can take it for credit. You can audit. If you are really into stormwater management, there's a great opportunity to learn more about stormwater management, the policies and the laws here, both from guidelines here in Montgomery County, from the state. Rick Scapiti from EQR, Environmental Quality Resources, who's going to be the instructor. And it's live, it's hands-on. Okay, so I know some people got a little tired of doing the Zoom thing. This is all out in the field. You're going to see Montgomery College stormwater, I guess, plan and our facilities there. You're going to see the good, and you're going to see the bad too. So, but anyway, and if you know Ann English, she'll probably participate in the class a little bit, and she'll point out some of the things that I know we need to do at Montgomery College to be more compliant. So if you have any questions about it, you can reach out to me. I'm going to stop at this point, stop share, and I think it's going to Renew, and she's going to update us on a few things. Thank you, Renew.
Thanks so much, Steve. Good morning, everyone. It's so great to see so many of you joining us live, and for those who will catch the replay, welcome also. I wanted to echo all of the thanks that Steve just shared with Ryan, today's speakers, the tech team, and everyone who's making the fall conference possible today. It's a big effort, and we really appreciate it. Also wanted to thank the committee chairs who have some big events coming this month, with the Harvest Festival, with Close Encounters getting underway. So again, I really encourage everyone to consider volunteering. I know that Carol has popped into the chat the link to all of our volunteer opportunities, and I see some committee chairs have also linked and mentioned opportunities as well. So keep an eye out on those. Final announcement today before I pass the mic over to Linda, which was to thank you all for the positive response that I received from the newly established Mission in Motion Task Force. We've had a few people write in via email, and I know Carol will put that link in the chat soon, just to share some interest in getting involved. We're in the process of finalising a survey for membership, so please look out on Groups.io, and there'll be plenty of reminders when that comes out, hopefully later this month. And the purpose of the survey is to really understand a bit better our collective experience of being a Master Gardener and how we feel collectively about how that fulfills the mission of the Master Gardeners. So please keep an eye out for that. And if you are interested in being a founding task force member, we'll be happy to hear from you as well. And speaking of the mission and serving our mission, I finally wanted to extend a note of thanks to Linda Barrett as our first Vice President. One of her responsibilities this year was leading the nominating committee and pulling together the slate that she will present to general membership today. I also wanted to thank and maybe preview a little bit that our current board, and I'm delighted to say that everyone is continuing on in 2024, which is super exciting. I'm so proud to be serving with this team. Everyone's so dedicated, and the program directors and all the committee chairs involved. I mean, you really make this organization happen. So I couldn't be more proud to be leading the group. So with that, I will hand the virtual mic over to Linda for the reading of the 2024 board member slate. Thank you.
Great. Good morning, everybody. So there we go. So our slate of officers for 2024 Master Gardener Board are, I'm gonna let you just look, same people that were here last year and I think the year before. The only change is our intern class rep, which is Christine Cotter. And that's the proposed slate of officers. We'll be voting on these at our November 2nd meeting, which is coming up pretty soon, next month. I do want to let everybody know that there are a good number of folks that are reaching the end of their limit on time limits, kind of like. So in 2024, folks will, be taking part, but then in 2025, we're going to have to look for a bunch of new people. So committee chairs, start looking for people that maybe can take your place if you're one of those people that's already served for 3, 4, 5 years. And maybe there are new people or old people as far as master gardeners that would like to serve as a committee chair or on the board. So please think about that for 2025. All right, I'm going to stop my share and give it back to Steve.
Okay, all right. At this point, let me see. I think we've run through our set of announcements, Ryan, and I think we've got a little bit of a time here, guys. If that's correct, then we're gonna do a little break here. So we don't have the dancing coffee cup up, but we'll probably break for about 10 minutes. So about a little bit of, come back at about 9:25, and we'll get ready to introduce our speaker, Mark Townsend, here in a few minutes. So we're going to take a few minutes. I'm going to turn my mic off, and I will see you guys in 10. Hey, Mark.
Yep.
So I heard you had some trouble, little car trouble, flat tire. That's frustrating.
Yeah, it sure is, but we made it just in time.
All right, that's good. That's good. And I see you got your screen pulling up, and you're wonderful, Mark, because you got the logo and everything there. Do you have the famous slide too?
I do have the famous slide. Yep.
Oh my gosh, it's great, awesome. So I gotta make sure I have the right colors now. So anyway, it's about almost 9:25, guys, and I said we'll probably start. So I think I'll just kind of start here in a minute or so, and I've got a little write-up about from Mark. There's a bit in the newsletter, and I want to always thank our folks for the newsletter, folks. I think we have the best newsletter in the state. That's my opinion. So, but I was going to read a little bit about Mark here. I went and Googled you, Mark. And so I did. So anyway, I think Mark's going to lead us off here today. He's going to be talking about soils. Some of this is, I think, going to be new. Some of it might be review, and it looks real good. I saw some of the slides. It's going to be great. And I think soils is one of the things that a lot of folks, a lot of gardeners, there's a lot of misinformation about things on there. Maybe things aren't quite understood. And I think Mark's going to here to help us out. So Mark is an agent associate of Frederick County. Mark joined the University of Maryland Extension in 2021. And as I mentioned, he's an associate agriculture extension educator. I think that's the formal title, like the long title for Frederick County. Mark is a Maryland native and has worked across the state on a diverse array of agricultural operations, including organic vegetables, row crop, multi-species livestock grazing, and dairy operations. Mark received his BS in agriculture and Natural Resource Economics from the University of Maryland in 2020. And he's currently working towards his graduate certificate in Geographical Information Systems GSI from Maryland. That's my daughter's taking those classes too, Mark. So she's in Maryland now. I think maybe one today. Mark's program is in the University of Maryland Extension, will focus on improving the economic, environmental, and social sustainability of production of agriculture in Frederick County and across the state. Welcome, Mark. Thank you. I think everything, the floor is yours. I'll let you do your thing. And we've got Ryan there who will hold the, she'll be looking in the chat box for your questions, and she will, if that's okay with you, I think we might have talked about that. She will, when you're done, she's going to give you the questions. I'll stop at this point. Thank you, Mark.
Well, Steve, that's terrific. That's a heck of an introduction. I certainly appreciate being here. Thank you for the invitation. Well, folks, it's great to be here with you today. So, as Steve mentioned, I have a bachelor's in ag econ, but really, I think my true passion actually lies in the world of soil science. I took a good many courses in soil science in undergraduate, and I really enjoyed them. I'm currently a certified crop advisor, so I work with growers improving their individual production practices, and I really rely quite heavily on the ideas of soil health and understanding the principles of soil management to make those decisions and to make those recommendations. So without further ado, I do agree with Steve in this, in that there is a lot of what I would consider, I don't want to say misinformation, but I think that there's a lot of information that has kind of come to the forefront of soil science that has been taken as a soundbite. And it's great that people are very much interested in soil health or, the concepts therein, but they're not actually kind of discovering the true scientific background. So I think today we'll talk a little bit about soil health, maybe go over some principles and maybe a little bit of the basics, as I'm sure you all know, excuse me, I have given this presentation to a variety of audiences. So I think for the most part, this could be a review for some of you, but I think that some of them, it's never a bad thing for a review. So first of all, what is soil health, right? There's kind of still this, undercurrent of uncertainty when it comes to that definition, right? How do we measure it? And then how do we create it? And also why? And so you see this diagram, we'll return to this diagram later, but I think it does a pretty good job of giving a brief overview of what soil health is in a nutshell, right? You have these sort of definitions, the interpretations, indicators, methods, principles, and practices all around the outside, and how it breaks out, subset of those, of the concept, the assessment, and the management of therein, and then that really defines the soil health and even further soil quality. So we'll talk about some of those. I know you see some weird things on there like bulk density, pH, EC, CEC, soil cover, things like that. We'll talk about how these relate. So again, right now, soil health as a concept is one of intense debate. There's great debate over the idea or the sort of like establishment of what is soil health, right? So really, it reflects kind of a change in thought process through the decades since the term was kind of first coined. But again, I think the best way to understand soil health, we really just kind of need a very brief review of the fundamentals of soil science. So, what makes up the soil, what happens in the soil, and how do we make our soils healthy are kind of the questions that we're going to answer today. So briefly, so the soil physical properties, right? So the ideal soil composition, right? Everyone has seen this chart. Every student of Soils 101, it's a breakdown of general components of the ideal soil, right? Soils are incredibly heterogeneous, meaning that they greatly vary. However, if we were to point to a specific point in a specific soil composition that would be best for crop growth, this would pretty much be pretty close, right? So you have about half of it being solid particles, right? Your organic and your mineral particles, 45 and 5% respectively, right? That's, that which is physically present as an object in the soil. Then you have the air and water, right? Those are the sort of the pore space. And roughly speaking, you want just about 50% of that, in a pretty even split between air and water as well. So the idea is, again, you just want to have an adequate volume of pore space relative to the physical particles that ensures adequate air and water movement throughout the soil system to ensure adequate biology and things like that. So, you know, you'll notice here that there's about 5% organic matter in this or ideal soil. That's not a hard rule. That's just kind of a guess for the most part. Really, for the organic matter is a topic we'll touch on today, but 5% is by no means the rule where you have to have 5%. You know, organic matter, as we'll learn, is in continuous flux in the soil system, whereby some soils may really kind of cap off at 1 or 2% organic matter. Meanwhile, other soils will have a 10 to 15% organic matter. So again, those mineral particles are quite important. We'll take a little bit of a dive into that. That mineral fraction is really what we see and feel. This is formed by the weathering of those parent materials, the rocks that lie beneath the soil. So millions and millions of years, those rocks begin to decompose through weathering, and those smaller particles continue to break down further and further until you get to the 3 main components of soils, and that would be sand, silt, and clay. So again, this is soil texture, okay? Your sand in this diagram, I love this picture here because I think it does a terrific job at really kind of explaining how large sand is in the soil system. You know, we think of soils as these living organisms and how, you know, beneficial they are. And when we start to think about their relative components, it's quite interesting to think about how large some of these particles are. So sand, you know, we can touch it, we can feel it, it's gritty in our hands, we can pretty well see the individual particles in between our fingertips. If ever you go to the beach, you pick up some sand, you can touch it, right? You can feel it and you can hold 1 grain in your hand. So that's pretty well this large area, right? Then you have silt, okay? This is a lot smaller, obviously, and it makes our soils a little bit fluffier, right? You can kind of feel it in something like a river, right? Those silty sort of deposits along a river bank, those are a little bit larger particles than, say, clay, but certainly much smaller than sand, right? Those feel like if you rub it between your fingers, it feels very smooth. There's no real grittiness, right? And then finally, we have clay. And clay is really the most important part of the soil. We'll begin to understand how clay actually plays a pretty outsized role in terms of its contribution to the soil system relative to its size. Clay is really roughly the same size of a bacteria. To think about that, an individual clay particle is about the same size of a bacteria, which is a wild thing to think about. But really, that is kind of an interesting comparison because really that is clay is a very, very important part of this. Now, clay, you know, I'm sure you've often heard, oh, the red clay soils or, you know, the black dirt or what have you. Clay really doesn't have a color, right? Clay takes on the color that the oxides or whatever mineral is sticking to it. So our soils generally tend to be a little bit reddish brown. That is not actually the color of the clay. Instead, that's a coating of iron and aluminum oxide. You have these breakdown, this weathering of these iron and aluminum containing molecules that continue to break down and actually coat the soil clay particles. If you think about it, it's just rust. We have rusty soils. So as I'm sure we all know, again, you know, clay, sand, silt, and clay, the relative proportion of each gives the texture, right? So this is the USDA textural triangle. It is a percent of each gives by weight, gives the percent volume, relative percent volume gives the idea of soil texture, right? So, you know, in this example, so we have something like, if we were to look at it, there's about 75% sand, about 15% clay, and somewhere in the neighborhood of 80 to 95% sand, of silt. So I think there's a good bit of sand in that, and so really the idea here is you're in that sandy loam territory. Now that word loam, I think, can often mislead us. You know, loam in essence really just means mix, right? It just means that there's a good mix. So it really doesn't tell you a lot. It just tells you kind of the dominant component of the soil, right? It tells you that there's a good portion of sand and then it's well mixed beyond that, right? I think the really kind of the important takeaway from looking at the textural triangle is looking at the percent clay. So if you watch how that scale slides up towards the tip of the pyramid, the sand being at the very lowest at below 10% clay. And as soon as you get to about, let's say 30% or so, 30% clay, clay becomes a part of the name. You have a sandy clay loam, right? Or you have a clay loam moving up a little bit north of that if you lose a little bit of the sand. So really, it only takes about 30% clay in that soil to really have a profound impact, just as the words of that texture give the idea of how much there is, right? So again, clay is a very, very important portion of our soil. So how do you do this at home, or how do you want to learn what your soil texture is? A really simple way of doing this is just the jar test, right? You can take a third of your soil, take a soil sample, take about a third of your of the soil sample itself, dump it into a jar a third of the way up, and then add the rest with water. And I would recommend throwing in about a tablespoon of dishwasher detergent. That really helps disperse those particles. You don't get nearly the right mixture if you don't put that in there. I would say it's a good idea to put some dishwasher detergent in there as well. So then shake it vigorously. Go ahead and set it on the counter and let it sit for 2 minutes, right? So that gives you, as the particles begin to settle, that lowest layer is going to be the gravel, the heaviest particles, that'll settle first. Then after the 2 minutes, you'll have the sand particles begin to settle. What you'll do is just measure the height of that above the bottom of the glass, which will give you the relative component or the relative proportion of sand. Beyond that, you would wait 2 hours, right? It takes a little bit more time for those finer particles to settle out. And so about 2 hours later, you'd have the height of the next layer, which would be the silt layer. All right, so then that gives you the relative proportion of silt. And then finally, you probably have to wait about 2 days to get to the clay. Why is that so long? Why do you have to wait so long? Well, clay is actually, as we talked about, it's such a small particle. Clay actually exhibits Brownian motion. If you're familiar with physics at all, Brownian motion is thermodynamic motion. And basically, it takes a significant amount of time for those clay particles to settle because it is, in fact, a colloid. It just exists and it moves around throughout. We'll return to this idea of colloid here in a moment. But a really good example of a colloid in everyday life is coffee, right? Coffee, as we drink it, is actually a colloid. There are these little tiny microscopic particles that float about in the coffee water mixture, and that is, in fact, a colloid. So I think that's an interesting thing. So then it takes you about 2 days for that to sort of settle out. Beyond that, then you should have water above that, say on day 3. So with that, at day 3, you can pretty much get a pretty decent estimation of what your soil texture is. You take the height of each layer divided by the total height of all of it, and then you multiply that by 100 for each of those layers, in which gives you a relative proportion of each, right? And then so then you would just consult back to the soil texture triangle to give you that estimation. Really simple way of doing it. The alternative would be to go to a lab. You can submit soil samples to a laboratory and they will tell you exactly what your soil texture is. This is kind of a down and dirty method if you weren't really intent on sending a $10 sample. This just kind of gives a real good rough estimate. The one at the lab will give you a much better estimate. That is something, they have Boyaco cylinders. They have far more advanced analytical equipment to do those sorts of things. So this is just a nice little way of doing it. So returning to the idea of a colloid, they are very small, chemically reactive and charged particles, right? So in our soils, these are clay particles and organic matter, okay? So this really brings us to one of the more important parts of clay. It is the seat of all chemical, well, I shouldn't say all, but it's the seat of many chemical reactions in the soil. Since clay particles are so small, they are colloids, right? They do exhibit that Brownian motion. Clay is negatively charged, meaning that it does exhibit a surface charge. This has to do with the soil forming process. As those rocks from millions and millions of years ago, as they erode away, where those smaller and smaller fragments begin to become smaller and smaller fragments, they actually have this sort of internal chemical change that elicits a surface charge. It's called isomorphic substitution, if anyone is ever interested. But basically what ends up happening is there's a charge imbalance on the structure of the clay in terms of its molecular structure, everything that's comprising it. So that creates this sort of charge imbalance in and of itself, whereby there's a surface charge, meaning that the clay itself actually wants to neutralize its surface charge, right? We all want to return to a low energy state, right? So that clay particle will actually, well, let me say it like this, some of those ions that float around in the soil will actually bind to a clay particle, or I guess zorb is the correct chemical term. But basically, this is the idea of cation exchange capacity. Cations are positively charged ions that float about in the soil solution, and the exchange is what happens when they move from the soil solution onto the clay particle itself or any other negatively charged particle in the soil. And then the exchange is when they come back off of it, right? And they are moved from one to the other, where a clay particle may decide, or, you know, it's not decide, there's no decision. However, it's like, here we have this calcium being exchanged for a magnesium in the soil solution, right? So the calcium will move on to the soil colloid, meanwhile, the magnesium will be pulled off, okay? So the cation exchange capacity, again, by definition, is the ability of the soil to hold and exchange nutrient ions, right? We think about it in terms of nutrients, calcium, magnesium, potassium, ammonium, things like that. Very, very important. This is a fundamental soil chemical property. And we actually use this a lot in terms of not only our agronomic recommendations, but in the garden as well. You know, if we have a soil that can hold a lot of nutrients, that means that we don't necessarily have to fertilize or spoon feed through time, right? We can put a lot of it up front. We can put some fertilizer or fertility up front, and the soil will actually kind of do the work itself. Alternatively, if we have lower cation exchange capacity, sometimes we may actually need to feed the crop a little bit more regularly throughout the season, right? So again, this is kind of a quantity of the negatively charged binding sites on those soil colloids. Really, it's just the amount of parking spaces that the cation can park onto. So I think about it like that. I think that's a pretty easy way of thinking about it. Which really kind of brings us to the idea of soil pH. So soil pH, and we'll talk about how soil pH and cation exchange capacity are related, but basically soil pH is incredibly important, right? When we're on this chemical topic, I would be remiss if I didn't mention soil pH. This is the master soil variable, right? It is the most critical role in determining the function of your soil. So again, returning back to your high school chemistry days, pH is potential hydrogen. It's a measure of the activity of the hydrogen or the concentration, meaning that it is the negative log, right, logarithm of the concentration of hydrogen ions. So with that, so it's a negative log, so there's an inverse relationship, meaning that the more hydrogen you have, the lower the pH, right? Therefore, the lower the pH, the more acidic. I know that's kind of weird to think about. I'm sure you all know this like the back of your hand, but it's worth mentioning. And the other thing to recognize is that there is an inverse relationship or sort of a identity relationship with POH, right? So that instead of potential hydrogen, this is potential hydroxyl, right? OH, that OH molecule is actually what drives the sort of base reactions, okay? So pH plus POH equals 14. Therefore, pH equals 14 minus POH, right? So if you know that and you have the sort of constant of 14, you know that you know that 7, dead in the middle, is neutral, okay? So anything below 7 would be acidic, anything above 7 would be basic, right? So with that, we'll talk a little bit more about how pH actually affects nutrient availability. As pH increases, cation exchange capacity will increase as well. Effectively, what's actually happening is those binding sites that we talked about, those binding sites are becoming open, right? The hydrogen that would have been on those binding sites is being exchanged out into the soil solution. And, you know, some of those calcium or potassium or other ions are being exchanged back onto it. You're effectively creating more opportunity for the soil to have more binding sites, right? This pH is outstandingly important for nutrient availability. Generally speaking, we like to see soil pHs in the 6 to 6.5 range. That's kind of that optimal range. You can see on this chart here, the majority of your ions are going to be active or at least available within this period of time. I think that, you know, obviously there are certain crops that fall outside of this rule. There are things like, you know, blueberries that really far prefer lower pHs, something like a 5.5 or below. Then you have others like alfalfa or even something like asparagus that actually prefer higher pHs, something like a 6.5 and above. But I think really the important takeaway from this chart is really looking at something like phosphorus, right? Phosphorus, you have these sort of zones where phosphorus is most available. And generally, like I say, that's about that 6 to 6.5 range. Below that, you have something like aluminum or iron, some of those compounds that we talked about that give soil that sort of rusty color. Some of those will actually bind to those phosphate ion and create aluminum phosphate or iron phosphate. So with that available phosphorus is tied up, whereby a plant really can't use that. Then you jump up higher in the pH, right? Calcium becomes your issue. Calcium actually will tie up some phosphorus. So really, we're especially thinking about phosphorus, maintaining that 6 to 6.5 range is super duper important, right? So not only is this affecting nutrient availability, it also affects cycling as well as the soil biology, which we'll talk about here in a moment. But we'll stay on the soil, the chemical properties of soil. Organic matter, again, we cannot go without talking about organic matter. Again, I think people kind of have a misconception of what organic matter actually is. If you've ever taken organic chemistry, it's not like the USDA certification, right? Organic in this context has nothing to do with the quality of something. Rather, it has to do with its chemical composition, right? So organic matter in chemistry is simply compounds that contain a carbon-to-carbon or a carbon-to-hydrogen bond, right? That's it. There's no quality additionality. There's just kind of the idea of ensuring that there is some sort of carbon-to-carbon bond, okay? So soil organic matter is about 50 to 70% carbon by weight, right? It's a really, really important thing to understand this. So organic matter are these sorts of compounds that were once living at some period of time, but however, they've started to decompose through time, right? So these are roots, these are bacteria, these are fungus, leaves, things that are slowly starting to break down in the soil. So there are also a couple of different pools of organic matter. There are like, there's a labile pool or an active pool, meaning that there can be some sort of flux in the soil system. You can have soil carbon move into different pools, whereby maybe a microbe might eat a little bit of it, or it'll be uptaken by a root or things like that. It can be used for fuel or something of a metabolic process. Meanwhile, there's also the sort of the recalcitrant factions. These are the organic matter particles like humus that give soil that sort of that darker color, right? Humus in this context is very much stable. It doesn't really want to go anywhere. It's been broken down to a point where your bacteria or fungus, what have you, they've gotten to the point where they cannot use it any further, okay? So again, these are incredibly chemically reactive particles. We'll see that here in a diagram here, but really, when we talk a lot about clay, clay is very important and the mineralogy of clay is very important. However, organic matter really drives these reactions further, okay? I consider this to some extent almost a catalyst. The more organic matter that you have in a soil, the greater your soil is able to function. You can have more and more processes go on because the majority of these processes are kind of biologically mediated. We'll talk about that role in here in a moment. But what I'm getting at is it is very, very hard to understate the role of organic matter in these soil systems. They are incredibly important to how they function, okay? So this is what organic matter looks like if you were to take a look at it through an electron microscope. This is a humus particle, right? So again, I say humus, not hummus, right? Hummus, right? We all know the delicious, Middle Eastern or dish that is, quite delicious from chickpeas. Humus, right? No, just one M. This is that stable form of organic matter. Okay. So as we can see in this image, look how complex and fractal this is, right? You have all of these holes and pores that comprise organic matter and these wildly complex and almost tangled mess. It looks like a spider web in a lot of ways, right? But it's fundamentally complex, right? And I think what's very important to note here is, we're looking at this through an electron microscope. We're at 2 micrometers, right? You can see that down in the lower left corner there, the indicator. At 2 micrometers, I mean, we're to the point of, you could probably see clay particles and things of that nature, right? We're just at such a minuscule scale. So again, organic matter, for as much as it does play these outsized roles, it is also very, very small. However, similar to clay, it has a very significant surface area, or what we would call specific surface area, which is the amount of area of that particle relative to its mass. Okay, so if you see all of these holes and channels and pores scattered throughout, you can see that there's a lot of, if you were to take like the mathematics of this and if you were to devise the surface area, this would be an incredibly large surface area, just because there are all these little channels that create additional little pockets, right? So moving beyond that, on the chemical side of things, organic matter is fundamentally complex as well. Now, this is, just a very, very simple diagram of what organic matter looks like on a chemical level, right? This is kind of meant to be your basic soil chemistry textbook, representation of that. The picture that we talked about, or the picture that we showed here just a moment ago, that would be, this molecule here would be just about one of those holes, right? So if you were to think about this repeating for millions of times over just to create that one molecule that we looked at, okay? So you see things like, you have an amine group down here, you have some hydroxyls over here. Look at you have benzene rings double bonded to themselves. Again, these are incredibly complex. There's a sugar up at the top, right? These things indicate that there are some sort of biological component, right? It once was living. You have these peptides, the sugars, the benzene rings, everything was once living and has been altered to some extent given the biological and microbial decomposition processes that exist in soils. So again, some of these things on organic matter, like these little ends, might be catabolized. There are microbes that want to use some of these ends or effectively catabolize for their metabolism, use some of that for their own benefit, gain energy from that. Okay, so this is also a state, this organic matter is always in flux. It moves through the soil system. We talked about that idea of labile organic matter or the active pool. So it moves through the system. It's not just stagnant, right? Humus would be that portion of organic matter that is stagnant. So its functions, it's really hard to understate the importance of organic matter, right? So it affects all three properties, or the larger properties of soil: the chemical, the biological, and the physical properties. So physically speaking, organic matter influences water holding capacity, right? It influences flocculation, porosity, and temperature, okay? So we'll talk just briefly here. So water holding capacity, you think about it, all of those channels that we saw and the pores that we saw in that visual description of organic matter, right? All of those channels and pores can latch on to a water molecule and hold it there, kind of protect it so it doesn't get taken up by, say, a root or lost through evaporation or even through the soil profile. So then next would be something like flocculation. This is just a fancy word for things sticking together, right? The idea of soil particles kind of joining together, right? Soil particles attaching to one another. So when you have that, when you have soil particles attaching to one another or joining to some extent, you actually create pore space. Since there's kind of a fixed volume, right? Everything that's in it, you move it over just a touch, or this particle touches the other one. And the arrangement of the particles changes, whereby you may actually have more space for air and water to move through that soil just by virtue of having increased organic matter that improves flocculation, right? So when we have water moving through the soil more readily, that would be something like infiltration, right? From the top, if you were to add water from the soil surface, it would move through the soil with relative ease, rather than say something like if the soil was compacted, right? The water wouldn't have the opportunity to move through the soil, rather it would just lay on top, and it would have a very difficult time moving down in the soil particle, moving down in the soil profile itself. And that's a function of porosity, right? We were talking about that. That's the relative degree of pore space, right? So as we were thinking about this earlier, we generally want to retain a 50-50 balance between pore space and the mineral particles in the soil. That's kind of best for crop growth. With improved flocculation, right, we get that porosity, we get that ability to maintain that 50-50 balance, okay? And then we also actually get some temperature buffering. If you think about it in terms of a desert, right? the soil surface of a desert generally remains pretty warm just because you have the sun beating down on it. It's very low in organic matter. It's quite sandy. Actually, a better example is if you go and walk on a beach, right? The sun's beating down on it. There's very low organic matter. It's just sand. My goodness gracious, I have burned my feet, walking in Ocean City times that I could count. You think about that and how very little buffer there is temperature. When the sun warms it up, it will stay warm. Meanwhile, if you were to go walk on, say, a muddy creek bank where there's a lot of decomposing plant material, and it could be a 95-degree day, well, sure enough, that is still probably a lot cooler than, say, that beach sand. Okay, so organic matter is very much a buffer to soil temperature. That's actually quite important for our biological processes. We generally want to maintain a certain level of temperature. We don't want to get too warm because we have soil microbes that will actually die when it gets too hot, very much in the way that we will have soil microbes die when it's too cold. So that buffer, that retention of heat and that dispersal of heat is very important. And that's why organic matter is quite important as that as well. So chemically speaking, we talked about cation exchange capacity, and going back to that image here, over here, cation exchange capacity, we were talking about how you have all those negative binding sites. Well, if anyone can recall back to the days of chemistry, these hydroxyl molecules are actually negatively charged. And there may be some degree of binding that can occur between your cations that float around in the soil surface or the soil solution and bind to these organic matter particles, right? So again, not only do we have cation exchange capacity being brought in through the mineralogy of the clay, but also through the proportion of organic matter. So in this way, when we think about amending our soil, when we think about improving our soils, organic matter, again, from a fertility perspective, is very, very critical. We can actually hold more nutrients. We can actually maintain some level of cation retention and improve cation exchange capacity by offering more negative binding sites for those cations to float around just by way of improving organic matter, right? So we have nutrient release as well. Organic matter, as it decomposes, as it is broken down by soil microbes, some of those ions will float back around into the soil surface. You have things like ammonia, you have things like nitrates that will slowly release back into the soil, whereby crops can pick it back up. That's vitally important, obviously, from the crop protection or the crop production or the garden production standpoint, right? We need to have that continual release of nutrient ions, and organic matter is a terrific way of doing that. The more that we can improve organic matter, the more nutrients that we can hold as well as release to our soils. So pH, again, that kind of has to do with that idea of buffering. Instead of the temperature buffering and the physical buffering, we now have a chemical buffering, right? So the more organic matter that we have, the greater resistance to change we would see in terms of pH. So if we try to shock the system, whereby we're trying to lower the pH of a soil, and if we have high organic matter, that organic matter chemically will slow the change over time. We actually won't see the jump or the spike in organic, or the spike in pH or the lower in pH, right? That has to do, again, with those sort of fractal edges that we talked about of that organic matter molecule, those hydroxyl ions that float about, right? Those are the things that will slow down and will keep a lot of those reactions from becoming too advanced. So then on the biological side, right, organic matter, like we talked about, is food for biology, right? These are things, again, that improve the nutrient cycling, nutrient availability, right? The majority of our reactions that occur in a soil are actually microbially mediated. So finally, organic matter is very much a reflection of our management. The more we can improve the way that we protect the soil, that we improve our cropping and production systems, we actually see pretty much increases in soil organic matter, okay? And really the most important part of understanding all of this is that soil organic matter and soil biology are intertwined inextricably, right? This is a very important relationship to keep in mind, that this is not only food for soil biology, but also habitat, right? Some of these particles, or some of these biological entities want to maintain and live in the soil, okay? So soils are alive, there's no other way of saying it, right? Microbes, although they only represent about 0.5% of the soil mass, the majority of the soil metabolism is due to soil microbiology, right? These are things like bacteria, protozoa, actinomyces, fungi. Those are the just very basic ones that kind of, flux or create these sort of cycles that exist where they will munch on some organic matter particles through the soil system and then create those reactions that we talked about. I love this statistic here. An ounce of soil can contain 28 billion bacteria, 3 billion actinomyces, 28 million fungi, and 3 million nematodes. It is an astonishingly diverse and outstandingly giant, astronomical, if you will, proportion of living things in the soil. If you were to take this over an acre of land, right? If you were to take a soil sample 6 inches deep across an entire acre of land, you would actually have more living organisms in that sample than there are stars in the universe that we are currently aware of. That is an astonishing amount of living organisms. It's very hard to kind of quantify that in a lot of ways. If we're being honest, that's the goal, right? We want to have that much, or we want to have that soil biology in that system. And we'll talk about here why. So again, soil biology is very much a critical part of that, right? You have these sort of relationships between these trophic levels, right? The organic matter is again, that food or even habitat for the soil microbes, right? The bacteria, the fungi, each one has their specific relationship with soil organic matter and with themselves, right? There are about 60,000 species of bacteria that we currently know of in soil organic matter, or excuse me, in soil biology. There's about 175 million species, or excuse me, 175,000 species of fungi that we're currently aware of. And again, this number is ever increasing, right? These are things that, this is a generally kind of a new topic in soil. Soil biology and the soil food web is crucial to the current understanding and the current way in which soils function, okay? So again, here kind of lies this idea of the philosophy, right? So if soils are incredibly diverse with a numerous community of microorganisms that have a profound effect on the intrinsic biological, chemical, and physical properties, then soils are interwoven with themselves as if it's becoming its own, thus implying some demonstrable quality. Soil health is a function of soil biology, right? This is kind of that main point. So when people talk about soil health, really, soil health is a comprehensive expression of the relevant soil physical, chemical, and biological properties. I love this definition. And this is a definition that is born by years and years of research and understanding through this process. This is not something that really kind of came about on a whim. So we've kind of talked over here on this right side of the table. We've talked about the biological, chemical, and physical properties, right? Then there are those processes that each one of these properties influence the processes, right? Gas exchange. Well, you have to have good physical characteristics of the soil. You have to have, adequate pore space and adequate water movement through the soil, right? Acid-base reactions, oxidation reductions, those are both the biological and chemical aspects of the soil properties, right? Well, then how do those processes affect our soil function, right? Soil functions would include something like supporting plant growth, right? Harboring living organisms, detoxifying contaminants, or recycling nutrients, those sort of functions, what the soil actually does for us. And I think soil health, is a perfect example of this, is that it's the capacity of the soil to function as an ecosystem, right? It looks at this in its entirety. It looks at the soil function, the soil processes, and the properties, and how it relates to create a well-balanced system, okay? So really, so what is soil health and where did it come from, right? The first reference to soil health was actually from the 1910 paper written by Henry Wallace. He equated soil health or soil quality to the idea of manure applications. It was, I guess, a novel practice at the time of folks throwing some manure before corn. And he noted that, the more manure that we put out there, the greater agronomic effects that we have. And he noted that over time, we actually have improved soil health. Okay, and so he actually, Henry Wallace went on to become a professor at Iowa State, and actually later became one of the first Secretary of Agriculture for the USDA. So interesting reference there. He was kind of the first guy to really say it. And then from the 40s, from that point on, we have this slow evolution of thought. Okay, in the 40s, we kind of have this idea of let's say Rodale and Sir Howard, right? The two kind of pioneers of organic agriculture. Those two folks really kind of brought the idea of soil health and tied it to plant health, and then therefore tied it to human health. They kind of created that link between soils and humans through this idea of organic agriculture. So they were kind of fundamental in defining maybe the practices or the ideas of soil health, or how it kind of relates on a broader spectrum. It kind of gained traction through that era, right? This is following the Dust Bowl and following a greater understanding of soil conservation. You see the creation of the Soil Conservation Service in the early 1900s. Then as it progresses, we see the adoption of no-till or other soil conservation practices, like even buffer strips, things like that on a large scale on the farm, okay? So then folks who have adopted this are seeing some pretty decent outcomes from their change in practices. And so economists of this era of the 1980s began to look at the value of soil health. How does it improve production practices? If we recall back to the 80s, this was again that era of significant turmoil in agriculture anyway. You have that stagflation, you have the farm crisis of the 1980s. There was a great deal of research that was devoted towards improving farm viability, right? How can we improve farm outcomes? And that would include things like, improving land values. And how does soil affect land values, right? That was an economic question. How do we retain or mitigate our input costs on the farm? Do we need to apply as much manure? Do we need to apply as much fertilizer, right? So again, that sort of economic analysis occurred in the 80s. Well, in the 90s, I think everyone said, well, not so fast. We still need to figure out what actually is happening. We need a definition for soil health. How does it relate? How do we define it, right? And so actually during this time period, I think there were 6 definitions of soil health. And the first one, I believe, was in 1990, and it continued up until about 1999, which is that final definition that I just kind of went over, that idea of the relevant expression, or the expression of relevant soil properties, biological, chemical, and physical properties, right? So then from the 2000s to about 2010, we kind of look at the practices that generate soil health. We talked about cover cropping. There was a good bit of research on no-till agriculture and the integration of cover crops. You see some folks at the Rodale Institute in Pennsylvania kind of adopt the idea of, how do we maintain a living root, or how do we ensure that we're still seeing that cycling of nutrients through time, right? Any of those practices to create that, right? And now here today, there's an incredible emphasis on soil biology. Again, we talked again about how soil biology in some ways is very much a reflection of, soil health is very much a reflection of soil biology. Here today, we see that kind of change. So again, now, most recently, there have been about 35,000 papers published in journal articles. If you do a Google Scholar search, if you go on Google Scholar and you type in quote, soil health, end quote, it will give you the breakdown of how many papers have been published, between decades. And from 2020 to 2023, there have been about 30,000 papers published that use the term soil health. Most of those papers have some sort of emphasis on microbiology, right? Those, again, we're now starting to see the general kind of evolution of thought, whereby we're recognizing the role of soil microbes in generating and governing those soil chemical, physical, and biological processes, the sort of the relevant expression of those as soil health, right? So then we also see a lot of emphasis on soil carbon and soil sequestration, right? Much of the research has kind of been based in how do we address global climate change, right? And so many folks have likened improving carbon sequestration or carbon cycling relationships to how in the soil, to how that would affect our current situation with the amount of carbon dioxide in the atmosphere. So moving on, here we have, again, this idea or this chart that we've seen in the front side. Most importantly, it's very hard to assess soil health, okay? Like we've seen, not just by virtue of the chemical processes or the physical processes, but those biological processes, the things that matter the most, we really just don't have as great a handle on those as much as we would like to. Like I mentioned, we have 60,000 species of bacteria that we currently recognize in soils. We have 175,000 species of fungi that exist in soils that we currently know exist. We don't know what they all do. We don't know how they relate to each other. And more, it's important to understand, well, how do those things generate soil health? Or how do they relate to the creation of soil health? Okay. And so really there isn't one good indicator of soil health, right? So if you were to take a test, it's not like you can ever take a soil health test that gives you a perfect answer. Okay. So, one thing that we can look at would be something like aggregate stability, which is the ability of aggregates to resist breaking apart, right? So that's a function of the microbial activity. How well did those microbes pull those soil particles and keep them together? But for the most part, that's a function of a lot of different things, right? Organic matter, microbial activity, composition, texture, moisture, management practices, temperature, where you are in the world, what kind of soil you're on. So it's not a terrific indicator for a broad analysis of soil health. So our current kind of ideas of soil health, we talk about, I would call in the 3 tiers of soil health indicators. Things that we really know, right? So that would be your tier 1, right? Things that we absolutely know have some sort of relationship or a significant relationship to soil quality and soil health, soil chemical quality and soil health, right? Your tier 2 would be something like, we have a general understanding, hey, this is probably a pretty known thing. Like, yeah, you look on this diagram here, and we certainly want to see soil stability index or macro aggregate stability. We want to see those things being very high. We want to see a large proportion of macro aggregates and see them being very stable in the soil system. That would be a good indication of soil health. However, like I mentioned, we know most of it, we don't know all of it. And then we get into that tier 3 indicator. These are things that are really on the forefront of the research, right? Soil microbial community structure, right? Or soil microbial DNA extraction and sequencing. So some of these individuals doing this research are actually looking at the genetic sequence of the soil and trying to define, well, how much of one proportion of microbe is there relative to the other. And that gets incredibly complex. And again, there's no real good tie between, well, if we have a 60% fungal to 40% bacterial relationship, therefore we're going to have good soil health. Well, we don't really have that yet. And so that sort of tier 3 indicator is really that next step to soil health, or at least measuring soil health. So again, here I think is a great example of, our current understanding of each one of those, right? So if you look at something like AWC, right, that second one on the list, that's available water holding capacity. So it would sustain biological diversity and productivity, right? That's that function, right? It stores and cycles nutrients and carbon, right? And it also regulates and partitions water and solute flow. Those are things that are those functions of soil health, or the functions of a soil that would be desirable to us, right? The relevant expression therein, okay? I think this is just a great indicator. I think it really touches on a lot of those ideas of how each test has its idea, right? Or what it's trying to measure. However, again, we're still trying to understand how it all fits together. So then really we get to this idea of, or this crux of the matter, where we need to quantitatively evaluate soil health. And really you can't manage what you don't measure, okay? And we're slowly getting better at measuring soil health. There are some new tests that have been generated to create almost like an assessment system. We'll talk about those here in a moment. We're trying to create indices, right? How do we evaluate things on a relative scale? And again, like I've mentioned, there's a lot of research and evaluation that still needs to go on before we have a robust understanding. So the currently available methods would be all of these here, and there's more yet that I have not listed. Personally, I'm a fan of the CASH system. That's that Cornell soil test that I'm sure you've heard of. There's also the Haney soil test, the Solvita, as well as the Maryland Soil Health Card. We actually have our own metric of evaluation. And I think it's pretty complex pretty comprehensive. It looks at both the physical, chemical, and biological indicators and gives a relative kind of scale of soil health. I think that it's a terrific indication, at least for our kind of rough estimation. We have it through the University of Maryland Extension, as well as NRCS. Any of your local NRCS offices has that. So, we talked about how soil health is kind of as a large spectrum, like what are the principles, what are the properties of soil health, right? We talked about how we could measure soil health and kind of the challenges therein, but really I think this is kind of the nuts and bolts of it, right? How do we generate soil health? How do we actually create improved healthy soil, okay? And so the first kind of overview of this was created by NRCS, the Natural Resources Conservation Service, back in about 2014. They came up with the 5 principles of soil health. The Noble Research Institute, as well as Understanding Ag, another organization, added a 6th. And we'll talk about those. We'll go through each one of those here, and it really kind of provides the basis for creating soil health. And again, I think the word principle is very important here, okay? These are management guidelines. These are overarching principles. These are not practices. It's not meant to be a prescriptive approach to soil health. No one's going to tell you you should put, cover crops in here. That's not going to be a principle. Instead, we're going to talk about how a practice could relate to a principle. So the first principle is soil armor, okay? I like it thinking out like this, keep the soil covered. You can say the same thing. I like soil armor because I think it really gets to it, right? Keeping the soil covered with living plants, residues, compost mulch, or any synthetic materials to protect it. Really, we're trying to control erosion or particle dispersion. The force that a raindrop hits the soil surface is, quite frankly, astonishing. On a mass basis, it seems like it's small, but on a relative comparison, I was trying to do some tricky math before we got here, but basically it works out to the Mack truck hitting a penny. There's an incredible amount of force that a raindrop exhibits on a soil particle, okay? So with that, you have this dispersal action. It's like an explosion. Some of the soil particles fly off the rails, and that's what really creates that erosive mechanism. Dislodging the soil particles allows them to flow more easily across the soil surface. We lose them, right? We also get, the loss of nutrients associated with that. Erosion is just an all-around bad thing. Beyond that, beyond erosion, we also think about how we were talking about soil temperature, right? Anytime that we have something covering the soil, we're limiting the amount of UV radiation that's hitting the soil itself, right? So this improves our soil temperature. We're not letting it get too hot. We're not letting it get too cold. Personally, I talk a lot about this with my farmers. Weed control. The best weed control is dark. Instead of having to go over it 2 or 3 times with an herbicide, for the most part, if we keep that soil covered, it's not going anywhere, and it's hard for plants to grow, right? And beyond that, like we talked about in that sort of the chemistry as well as the physical aspects, right? That coverage of the soil is a habitat for soil organisms. The second principle would be minimizing disturbance, okay? Reduce the incidence of mechanical, chemical, and biological disturbance. Anytime you're disturbing that soil, you're changing the dynamics therein. Tillage, it's a love-hate relationship, all right? Some things are great about tillage, some things aren't. And one of the primary issues with tillage is that it actually opens it up to too much oxygen, whereby you have this microbial decomposition. You have this respiration that just ramps right up because you have all of this influx of oxygen. Those microbes are going to want to eat all of that organic matter. They now have the opportunity to do so. They need oxygen for that respiration, okay? Which is fine to some extent, right? We all need to till just a little bit. But for the most part, that kind of conservation tillage or limiting the amount of chemical or mechanical disturbance we can have is going to be a good thing, right? This could be something like no dig gardening in the garden anytime you're trying to minimize the amount of time you're flipping soil, okay? Also chemical disturbance, right? So herbicides, fungicides, insecticides, commercial fertilizers, anything with a high salt index or anything that effectively kills alters that soil system, right? You're disturbing its natural function in doing that, right? So I like to talk about integrated pest management with my growers. Sometimes you really just don't need to apply that insecticide. Sometimes you can get away with not doing that just because that damage to the crop is really not going to be economically viable, all right? And then the last thing I talk with my growers with is controlling the grazing, right? You can have biological disturbance, right? So things like overgrazing or biological or incidences born by nature would therefore slow that processes down just because you're further disturbing the soil system. The third is maximizing plant diversity. Anytime you grow more species of cash or a cover crop, you're really kind of eliciting more and more soil microbes to function, right? The more living roots, the more diverse living roots that we have, the more opportunity a microbe has to function, right? It's food throughout the year. It's potentially another home, right? We also kind of control the soil-borne diseases, the more we can increase those rotations or alter them with other things, we suppress some diseases. So I'm thinking in particular of corn diseases. You know, oftentimes we have some root rots or even some pests of the soil that really are mitigated when we have effective soil or effective crop rotation and a diversity of plants growing even in one space. Okay, and the fastest way to improve microbial diversity is through plant diversity. That's the easiest way of doing it. The next would be maintaining a living root. Anytime we can keep a plant growing throughout the growing season and even into the winter months is going to be a good thing, right? It's more food, it's more control of erosion. We're still kind of mitigating that speed at which the raindrop can hit the soil surface. We're trying to alleviate compaction to some extent, right? There are certain crops that we can plant that have a really deep taproot or have a pushing effect or even a fracturing effect of the soil surface, whereby those compacted layers are slowly mitigated over time, right? So maintaining a living root augments the soil health kind of outcomes. Fifth is integrating livestock. This is a big one for some of my growers who are really trying to push the envelope with soil health, but for the most part, this is something that's very context dependent. Sometimes you really can't do this, right? I don't have chickens, I don't have cattle, I don't have the ability to integrate livestock. Anytime you can do that though, you're gonna see improved weed control, right? You can get better cycling anytime, or nutrient cycling, anytime that you're also adding an organic form of nutrients, say through manure or through compost or things like that. That's going to be a solid, right? And really, it's profit per acre. That's what I talk to about my growers, right? You can stack enterprises. You have multiple things going on at the same time. And then sixth would be knowing your context, right? So again, we talk about how this is not a prescription. This is rather a principality, right? We're looking at the broad spectrum ideas, right? So context would be knowing what you have on your operation, what you have in your garden and what you're willing to do, right? So these are your soil type, your skills, your resources, things like that, okay? This really governs what you're willing to do in terms of your practices. And it really is up to you to implement these principles, right? And how it would best suit your needs. So why even soil health? Why does this matter, right? The first thing is always going to be money. I always talk to my growers about this. You know, we talked about that the time period in the 80s where you have that sort of economic evaluation of soil health practices. Really, this is kind of that benefit, right? Soil health is by and large one of the easiest ways that we can improve resiliency on the farm, improve that bottom line, lower the amount of inputs that we're putting into the system, and instead just kind of improve what we have and lower our costs. Next would be increased interest, right? So we have a greater understanding from the public, from governments, from corporations, you know, climate action, carbon markets, the regenerative food system. Really, there's going to be, I think, probably more and more attention paid to this idea of soil health through time, and potentially premiums therein for products that are raised in organic, or excuse me, regenerative, if you want to use that term, or at least a soil health conscious focus. And then finally, it's risk management. You know, it really kind of creates that sort of resilience in our farm or on our garden, right? Anytime we can, you know, improve soil health, I talked about how a lot of those things are a buffer, right? Buffer to temperature, buffer to rainfall, buffer to weeds, right? It really mitigates the kind of negative risk associated with that. So I'll leave it at that. Soil health is really kind of the benefit that I really like to talk about with those sort of management practices and how we can kind of generate those through time. So with that, I mean, are there any questions?
Thank you, Mark. Thank you so much for sharing your expertise today. We did have a few questions pop up in the chat. Someone's wondering if you can have too much organic matter in a garden, and if so, how much is too much?
So yes, you can. I think that anytime that you approach a point where, so let me say it like this, there is no one answer. I'm not going to tell you 17% organic matter is a negative, or I'm not going to tell you that 7% organic matter is a negative thing. What I will say is when you get to the point where you don't have the structure of a soil that has a larger mineral fraction, right? We talked about those solids, right? So the mineral fraction, the organic fraction, you need a good balance of those. If you're seeing that there's an erosion or sort of the what I would call like the falling in or the caving in of a soil, that would be a concern, right? I think that beyond that, you also need to have that mineral for the structure and the pore space development of that soil. So there isn't really a good answer for that. I would say it depends, but anytime you start to see negative consequences to that, that would be the time that I would say, okay, you know, it might not be a bad idea to go dig up some soil itself and then put it in your garden.
Thank you. Does the meaning of soil health depend to some extent on what lives in and on it? So soil health in a, say, tropical forest might be different from soil health in a desert. How do they relate?
That's absolutely right. Yeah, I think that there is and we talked again about that idea of context, right? Context is crucial in this. There are going to be certain things that change through time. So if I was trying to generate healthy soils on beach sand, I'm not going to see 5, 6, 7% organic matter, right? There's going to be way too much activity in that soil, way too much water movement, way too much oxygen for any sort of deposition of organic matter to kind of maintain that. So, and beyond that, also the microbial communities of, say, a rainforest and a desert are vastly different, whereby the soil health outcomes that I would say, the improvements that you would see in one would be far different than another, right? So yeah, there's a pretty significant difference between the two of them.
Okay. Could you address the issue of potential disturbances to soil microbiology and the use of plastic mulches such as tarps and landscape cloth? There have been a few articles regarding that in the fact that there's a decrease in microbes and how they alter the soil flora and fauna.
Yeah, that's absolutely right. So I'm not going to say that it's a bad thing, right? And again, it depends on your context and what the goal of that landscape fabric is doing, right? So, you know, on a commercial basis, or even just if you were using it as something like a solarization, right? So if you had a cover crop laying there and you threw a tarp over it, a white tarp, and you really just wanted to kill that cover crop in an alternative method without an herbicide or mowing it or something like that, you're going to kill a lot of soil bacteria and soil microbes as well. That's just the nature of the beast. I think that it is, again, context dependent. I don't think that plastic is necessarily the enemy. I don't think that it's a bad thing. I think that when used in moderation or when used for a specific purpose, I think that it could be an incredible benefit. I would argue, however, that you could implement other practices to achieve some similar goals. So if plastic is kind of your weed control strategy, you might want to think about having a diverse cover crop that you can lay over top of the soil surface that prevents, say, light or water from really kind of reaching those weed seeds from germinating and preventing them from germinating. So I think that's positive. However, again, you know, nothing is ever all bad and nothing is ever all good. So I think that's, again, context dependent.
Thank you for that. We have someone asking, as a non-scientist and concerned citizen, I look at the farms diminishing in the county, and they're wondering where they can go for up-to-date research and best practices on soil health within suburban development, such as a newsletter or a journal, something to that. Is there any recommendations you could make?
You know, so I'm unaware of anything. Well, let me clarify here. So am I understanding that the idea is more so you would like to see more soil health topics in the garden setting, or is that more of like you would like to see or learn more about it, of how it applies to the farm? Could I have some clarification there?
I believe it's how it applies to the diminishing farming in the county.
Yeah, so that's an interesting thought. I think you could make an interesting correlation there. I'm not sure I would extend it too far. I think that there are much more exogenous or even more important factors that affect farm retention. I think that soil health and, you know, these sorts of practices play a pretty significant role. I think that, you know, as we talked about, you as a farmer, you know, you can limit your input costs, or you can have, you know, higher premiums paid to you for, you know, your product, and that may to some extent offset some of those negative consequences, the negative economic conditions that currently exist. However, I would say that for the most part, a lot of this is going to be market driven just by virtue of land prices and things like that, where farmers are just stepping out because they physically cannot, acquire any more land just by virtue of the extreme cost of land. I think if you're interested in learning more, obviously Extension has some resources. I would point you to some of the folks at Understanding Ag. That's a website and a organization that does some outstanding research as well as some outstanding advocacy on behalf of regenerative agriculture and soil health more broadly.
Thank you. Here's an interesting one. Are you looking at the effects of jumping worms removing organic matter in the soil?
So I am not, but I do think that is important, right? So again, that idea of the soil food web, right? You would need to have a balance on the other end of that trophic level. Is there something that's willing to eat those jumping worms to improve that sort of natural balance? And I don't know if there's an answer there yet. I don't think that worms are ever going to be considered a bad thing in the sense of, I'm never going to tell you, oh, that specific thing is bad and you need to get rid of it. Well, maybe not. It's maybe a question of balance and how it relates to the larger system.
Thank you. Here's a question regarding nitrogen availability. It moves and changes during the year. So how can we organically increase the nitrogen in the spring when it's typically low?
Yeah, that's a good question. So we talked a little bit about temperature and as well as microbes. So as you alluded to, you're not in say early relatively low just because you have soil microbes that have not yet woken up, right? They're still slow, they're still dormant, they're not feeding and releasing those nitrogenous compounds near to the extent as they would later in the season. So a good way to do that is just supplying the food to begin with. So something that is naturally kind of high in nitrogen or that can effectively release nitrogen in the soil through decomposition as it's ready is a good step. So I would say something like a leguminous cover crop, anything with like clover, alfalfa, sun hemp, anything like that can overwinter and give you that nitrogen going into the growing season is a good thing. Oftentimes I talk a lot with my farmers about, hey, it might not be a bad idea to throw some hairy vetch in with some winter rye before your corn, right? Corn is a heavy nitrogen feeder. If your cover crop overwintering has a good supply of nitrogen or at least fixes nitrogen through the atmosphere, you might actually end up supplying a good chunk of that nitrogen through the season just by virtue of having that cover crop there.
Is it too late to plant a fall cover crop? And if it isn't, what cover crops would you plant? And if it is too late, what would you plant in the spring?
So I don't think it's too late. Personally, I fall within the idea of if you can put it out there, put it out there. Winter rye in particular is especially cold hardy. It may not germinate here in the fall, especially as we get later. I've seen rye planted as late as December the 20th that doesn't germinate in the fall or doesn't germinate that year, but the next year going into the spring, once we start seeing warmer temperatures, jumps right back up there. However, we're still well within the optimal planting window of rye. I would say up until maybe about the 1st of November would be about the time that I might start thinking about, we might be getting a little bit later, and I might save a little bit of money and go with something like a spring cover crop. But for the most part, I think we're fine now. I think rye is a great cover crop. Clover, hairy vetch, common vetch, things like that to supply that additional nitrogen are terrific. If you want to get crazy, something like an African winter cabbage, that's a brassica, that's a really interesting crop. It takes a while to really understand how it works, but it's an interesting one. Great cover crop. And in the spring, I would say something like clover with oats. Spring oats seeded early, a really good jump to the early season growth, and then it might provide some cover moving into the early part of the growing season.
Great. And along those lines, does succession planting in the same locations of different crops through the year deteriorate the soil health, or is there a benefit to that succession planting?
Yeah, far from it. Succession planting is very, very important. I think that's a terrific practice in a lot of ways. We talk about how important that is. So succession planting kind of covers a lot of the soil health practices, right? We're getting the plant diversity, right? You're planting one thing after another, you're maintaining a living root, and you're covering the soil, right? So those just 3 boxes checked there on the principles of soil health. I think that's an outstanding practice.
Could you explain the value of biochar, and do you recommend adding mycorrhizal fungi when planting trees and shrubs? And can you correct me on that pronunciation?
Yeah, mycorrhizal fungi.
Okay.
So I'll first start on the biochar question. So biochar, for anyone who's unfamiliar, is pyrolyzed carbon. So pyrolysis is heating any carbonaceous material to the point of decomposition without oxygen, right? A really simple way, charcoal is a terrific example of biochar. Basically, you're creating, it's a Maillard reaction, but basically you're decomposing some of those carbonaceous bonds, and it's effectively creating a myriad of pore space and binding sites. So biochar as a soil amendment is I think it's a very interesting topic, and there's a lot of research being done on it. For the most part, it's a good thing. I'm not going to say that it's going to solve all your problems. I think that it's a pretty good practice to do. I don't necessarily see the touted benefits as they have once, kind of lauded the potential of biochar and how, outstanding it's going to be. I think anything that's improving soil carbon is going to be a good thing. It gives another point, like we talked about, for those binding sites in the cation exchange capacity, more home for microbes, greater water retention, terrific. Is it going to be the solution to all problems? No. The mycorrhizal fungi, to that point, that is a fungus, right, that we alluded to, one of the 175,000 species that we currently know of in soils. Mycorrhizal fungi are terrific. They are vitally important for phosphorus mobilization. Mycorrhizal fungi will actually associate with plant roots and then send out a fungal hyphae, almost as if it's its own root. And there's almost a superhighway between a plant root and the fungi itself, where they can exchange nutrients very easily. They're incredibly important to soil systems. It is unlikely that if you apply mycorrhizal fungi in, say, like a jug or a solution or as a compost that is supposedly inoculated with it, it is incredibly unlikely that they will still be living. I wouldn't waste your money. This is a topic right now in agriculture that is very, very contentious. There's a greater adherence or a greater acknowledgement of soil biology, as we talked about, and many times folks want to go out there and spray a biological amendment. Well, the only trouble with that is, again, we talked about the vast array of microbial species. How do you know that one species of mycorrhizal fungi or bacteria or whatever you're applying, how do you know that one in 175,000 is going to be the right one for you? I don't think you do. I don't think it's worth it. I think the better way of doing that would be naturally improving your soil through your practices, through your management practices, rather than, say, applying something just off the shelf.
Thank you. One last question for you, Mark, about cover crops. And it's a two-parter. Does clover add nitrogen while growing or only when it dies? And then should the cover crops be left to decompose, or should they be pulled up before planting other crops?
So great question. So we'll talk about legumes just here briefly. Legumes, they basically do, well, let's back up. Legumes are plants like peanuts, clover, beans, alfalfa, right? And basically what they do is they absorb nitrogen, or N2, nitrous oxide, the nitrogen gas that exists in the atmosphere. They pull it down into their roots, and there's a symbiotic relationship between a certain species of bacteria and the root of that plant. And they create these small little nodules on the root. If ever you pull up a clover plant, you can see these tiny little white dots scattered across the roots of the clover root itself. It's outstanding. It's very interesting. But basically, that little dot is the sort of fertilizer factory for that plant. It's that slow fixation of nitrogen. What's happening is those bacteria are taking in that N2, splitting it, and creating amino acids anything using nitrogen that the plant could then use for itself. So as the plant grows, it's performing that action, okay? The idea of nitrogen being released or nitrogen supply is a function more so of degradation of those nodules on the roots. So you almost need it to die, but I don't want to be too prescriptive in this. It is a flux, right? Some roots die, some roots live, some roots die, some roots live as it is growing itself. So what I would say is that when you have clovers in that system, you are in effect supplying some nitrogen through nitrogen fixation. And we see the vast majority of that nitrogen become available when the plant itself dies and starts to decompose. With that being the case, I would not recommend pulling up the clover or vetch or what have you if the goal is to maintain some degree of nitrogen fixation in that soil or supply nitrogen for that crop. Instead, I would say any other termination method would be good, roll or crimp, heck, even a herbicide in some instances, anything to just kind of kill that, improve or start that decomposition process and allow for that nitrogen release. Alternatively, however, you can pull it up if you need the space to plant into, obviously, but I would say, for the most part, I would say leave them there.
Thanks again, Mark. Thank you for sharing your expertise in this topic. It's so informative and helpful. We really appreciate your time. And I think that's for now. We're going to wrap it up. And we're going to take about a 10-minute break, get coffee, whatever you need to do. And we're going to circle back at 10:50 with Andrew Risby. And he's going to further educate us regarding plant nutrition and nutrient availability. So we'll see y'all back here by 10:50. Thanks. All right, it looks like it's about that time, 10:50. So I'd like to introduce our next speaker. And that's going to be Andrew Risby. Andrew is a principal agent and extension specialist for commercial horticulture at Y Research and Education Center at Queenstown, Maryland. And he's affiliate faculty with the Plant Science and Landscape Architecture Department at the University of Maryland, College Park. He did receive his MS in 1993 from the University of Maryland, Eastern Shore, and has earned his doctorate in horticulture in 2004, where he conducted research on plant nutrition and nutrient management. Andrew's current research interests are plant nutrition, irrigation management, sustainable alternate crop production, and green roof systems. Great topic. Good morning, Andrew. Welcome.
Morning,
Thank
Ryan.
you for joining us.
Thank you for inviting me.
So if you're ready, you could share your screen and
Yeah.
start your presentation.
All right. Okay, everyone see my screen? My program look good?
Looks great.
Okay. So first of all, let me just move some things around here. Okay. So today's my present. First of all, good morning, everybody. I should be polite. It's great to be here with all of you and participating in your program. I'm sure many of you have already went through my my plant nutrition program and that I've had for trainees. This program today is more of an applied talk, so that you can take what you've learned from your nutrition program that I get, plant nutrition program that I gave, and take this into the actual environment applied wise. So first of all, I just want to make sure everyone knows that our extension programs are open to everyone. And it's not just because it's the law, it's because what we want to do for all of you. So today I'll be discussing diagnosis of plant nutrient deficiencies, and we'll try to get into water stress too in the landscape. And I'll kind of start this out kind of framing all of this is if you ever were curious about what's going on in the landscape, taking notice is how you see how plants are growing. You can see plainly that the plants will show you that something's wrong in their environment. And the trick is determining if those issues are nutrient problems in the first place. And so in the next hour, I'll take you through kind of an educational tour of landscape problems, give you a decision-making guide to help you decide if those problems are caused by nutrients or other things. And then we'll discuss some of the typical nutrient issues I see in the landscape and explain why they may be occurring and what you can do about them. So the first set of slides, I'm just kind of going to take you through all the different things I see in the landscape. This is a birch tree leaf. And I could certainly point out to a lot of peculiarities on the shape of the leaf to think that it could be a nutrient deficiency. It could be a chemical drift, or it might be something different. If you look very closely at the leaves, you'll see stippling on those leaves, and in fact, it is very similar to what's going on with this leaf. Although you don't see stippling, the same problem exists with this particular plant, which I think is a hydrangea. So if you look really close, you won't see much other than maybe these problems, but you need actually a microscope to see the true problem, which is it's the aerophyid mite, which are causing these deformities in the leaf itself. So we have insect problems that do this. This is a redbud. Has anyone ever seen anything like this in their landscape before? If you live near agriculture, you would. This is due to phenoxyherbicide toxicity. And the plant actually, the phenoxyherbicide was not sprayed on this plant, it was drift. So these things occur often in agricultural areas. Anywhere where you have farming, you might see these sorts of deformations of leaf material, which is not nutrient related or insect related. It's chemically related, and so it's very similar to what you saw with the other two leaves on the previous slides. Again, this is an oak leaf, a group of oak leaves off of a branch. Same typical deformity. You might think this could be a phenoxy toxicity, but in actuality, it's a disease. It's an oak leaf blister. So all of these things are very interesting. This is a bacterial leaf scorch, which can often look like a water stress towards the midsummer areas. So all of these symptoms can look very much alike, and show very similar symptoms. And so the task you have at hand is to try to figure out exactly what's going on. This is a pansy in a production system, greenhouse production system. It again shows very similar leaf curling, but this is actually boron deficiency. So this is the first nutrient deficiency you've seen in these set of slides. This was taken in a landscape in Michigan. This is a viburnum, and I thought that at first this was a variegated viburnum, and it's not. This is actually a nutrient deficiency, and it's most likely an iron deficiency. And this is a tree that has iron deficiency. You'll see a lot of oaks and trees like these planted in streetscapes where the soil's not quite right for full nutrient availability. And in this case, this is another situation where iron deficiency is a problem with this tree. So there are strategies that you can go about trying to figure out whether these issues that you see in the landscape are either nutrient deficiencies or not. And so obviously the idea is to determine that problem. And the first question you need to ask yourself is whether this is a biotic problem or an abiotic problem. And when I talk about biotic problem, I'm referring to, is it a disease or a pest? And you can kind of hone in on these, whether it's biotic or abiotic, just to see what kind of patterns you're seeing in the landscape itself, with the plants that you're looking at. If the problems are scattered or localized, meaning that there are some problems here, some problems there, and especially if they're randomly distributed, or if they're distributed on one particular plant, it's probably a biotic problem. It's a disease or a pest. If it's abiotic, it's either chemical damage or a nutrient deficiency, you're going to have non-localized, non-scattered problems. It's going to be throughout the whole planting bed, and more of a uniform distribution, and multiple species may be involved. And this is because when it comes to chemical damage or nutrient deficiencies, more often you're going to have plants that are all exhibiting these stresses. Certainly, with chemical damage, some plants are more susceptible to chemical damage than others. Oaks, redbuds, grape leaves are very, very sensitive to phenoxy herbicides, and other plants may not be. But when you have these abiotic factors, it tends to be more of a spread in more uniform distribution. So when you strategize, the whole point of this is to define what the problem is and to understand what that problem is. Is it a problem? First of all, your plant varieties have a variety of different shapes and looks. There could be cultivar differences which you might have. Again, you can want to look for patterns, uniform or random patterns, abiotic or non-abiotic. And so you gather that information. You do your scouting. You look for insects. You look for diseases. You ask questions. This is a program that I give my landscaping industry members. And when they go out and they're looking at their landscapes that they're taking care of, sometimes they get them when they're brand new, or sometimes they inherit them from adding business clients. And so you ask questions. You ask questions about when plants were put in the ground, when these symptoms started appearing. Have they been here for a long time, or have they been just showing up recently? You eliminate the unlikely possibilities, and you consult resources. What's amazing is that we've got these little computers in our hands nowadays, and we can access all kinds of information out there. And so there's a lot of resources online that will help you diagnose problems in the landscape. And of course, one of the most important diagnostic tools is a soil test. So if you're having problems in your own landscape, or you've got friends that are having problems, then maybe one of these things to do is to get a soil test, and to see if there's a nutrient problem in the soil itself. Once you are able to figure that out, and not only soil testing, but if the soil test doesn't tell you much, because sometimes it doesn't, then you go directly to the plant, and you take leaf samples that way. If you suspect it's a disease, you can send it to a laboratory. Certainly in the commercial industry, the commercial horticultural industry, we have our diagnostic lab at the University of Maryland, which is used quite heavily. So there are options out there for us as scouts for landscaping. Taking that action, fixing that problem, use your resources available, and document everything that you see, so that you can go back, and if you see those problems again, you can go back into your notes and you can recognize, I remember I saw that several years ago, and I think this is what that is. So the causes of nutrient disorders, there's plenty of them, but most of the time it has to do with soil quality. And Mark, my colleague, had given a fantastic presentation an hour ago regarding soil health, and specifically getting into soil chemistry. He talked about one of the major factors of nutrient availability in the soil, and it has to do with pH. pH is a main driver of nutrient availability. So making sure that the plants are growing, their roots are growing in the right pH of soil is very important. On top of that, texture and structure. Mark talked about those important factors of soil health. Texture and structure is part of that. Compaction. If you have compaction, you're not going to get the right aeration. You're not going to get good water infiltration. So these problems can exacerbate issues or be the cause of issues to begin with. And other management things might come up. What sort of amendments are being used in the soil itself, either pre-planting or post-planting with mulches and things like that? These could bring in problems. And that's why communication with the landscape owner is always good, to understand what's going on in the management of that in that crop, right? So the location, there's also that issue of location, the right plant, right location. You know, we don't really want to put our azaleas up against the foundations of our houses, primarily because the foundations are made with cinder block, brick, which have a tendency to leach carbonates out into the soil, and they raise the pH, and therefore, you know, sometimes our azaleas might get a little deficient in certain micronutrients because the pH of the soil is being raised by the foundation components of homes. Right plant, right location is very important. The history of plant care or management is also an important factor. Again, it's communication with the landowners and or the landscape owner is also extremely important. And then, of course, the quality of the plant going in to the landscape. Was it in good shape? Was it root bound? You know, are those was the plant did it have enough nutrients in the plant stored up before it was put in the landscape? Things like that are factors that can affect the way plants look in the landscape. And then, of course, as I mentioned before, soil amendments, and I think soil amendments can have a huge impact on plant health. And certainly, you know, Mark talked about organic material and the importance of having organic material in soils, and also I agree with them. My lectures with plant nutrition, I really focus on organic material and how that adds to soil fertility. But not all soil amendments are the same. And oftentimes we might be making a compost or getting a compost from someone, buying a compost, which may have elevated levels of certain nutrients, which may cause imbalances or may cause toxicities in imbalances with other nutrients, which can cause deficiencies in its own right. So it's one of those things where you have to really be careful about what amendments you put on your landscaping. Making sure that those amendments aren't going to carry something in with them that might cause nutrient deficiency problems in the future. So, you know, your tools for diagnosis, that soil sample is what I talked about at first, and that soil sample is really key. And the soil sample, the analysis will give you pH, organic matter, your electrical EC, which is electrical conductivity. If you certainly if you have a substrate, not a real soil, but an organic potting media. Oftentimes we're growing plants in containers. We shouldn't be using real soil in those containers. We should be using organic potting media. And in the nursery industry, oftentimes organic potting media is being tested in electrical conductivity, or the amount of salts you have in that media is an important factor. Nutrient concentrations, of course, that's all part of the soil sample itself. Sometimes sodium is a parameter in the soil test if you ask for it. Sodium is a toxic element to plants. It's typically in soils to begin with, but at certain levels it can be very toxic, and we all know where high levels of sodium can be located, right along sidewalks or roadways, especially in our area when we get a lot of salt being applied in the wintertime. So that soil sample is very important. You can get pH probes or salinity probes that can help you determine those factors immediately. You can do take a soil sample and get the pH of any soil just by adding a little bit of distilled water to a soil sample and making a saturated media extract or just making a slurry. Leaf samples I spoke of earlier. The soil sample tells you what's going on in the soil, but sometimes it really doesn't tell you what's going on in the plant. And the leaf sample will just basically tell you what the problem is. It's just that a soil sample is very inexpensive and a leaf sample is not. And if you're ever curious about taking leaf samples, there's a process of doing it in labs. Typically, soils labs will do a nutrient analysis with leaves. There's information out there that tells you based on the types of plants, your varieties, your cultivars, and the species that you have, just the range of where nutrients should be in that leaf sample to give you an idea if you have a deficiency or a toxicity. So when you do leaf samples, you want to ask for all the nutrients in a leaf sample. The analysis essentially is you want to ask for all the nutrients, including molybdenum, especially if the pH of the soil is low. Typically, we don't see a lot of molybdenum deficiencies in soils. You always want to sample the youngest but fully expanded leaves. So the leaves that are the most recently fully expanded are the leaves that you use in a leaf sample, primarily because they indicate mostly they are the best indicator of any deficiencies or toxicities that you have. Now, when it comes to a soils test, okay, I think that I've in my plant nutrition program for trainees, I really go over the soil analysis and all the different parameters in there. But I'm not going to do that a lot. I'm not going to really focus on that today. But I just wanted to kind of remind you of the things that we see. Of course, with the method of extraction that we have in the soils test, it's called a Mcmg, which uses several different types of chemicals to pull the nutrients away from the soil particles and then make them soluble so that they can be analyzed by analyzing machines. And so what you notice in typical soil samples, okay, you've got phosphorus and potassium, you've got all your macronutrients, all your micronutrients, typically except for molybdenum and nickel. But with your macronutrients, there's one macronutrient that you don't see on a typical soils test, and that's nitrogen. And the reason why is because, as someone had mentioned earlier when asking questions to Mark, is that nitrogen is extremely labile in the environment. It changes from day to day. And what you get as far as a nitrogen result from a test that you sampled a week ago may not be there when you finally get your analysis. On top of that, the chemicals that are used for Mcmg extraction are full of nitrogen. So typically you don't get a nitrogen test when you are doing soil analysis. There's also organic matter, and that's LOI is loss on ignition. So they will heat up your soil and they will determine the weight difference and figure out how much organic matter was burned off. And then from there, they can give you an estimated nitrogen release on how much basically that organic matter will supply nitrogen to the plants on a pounds per acre. Soil pH, of course, is the first thing we all go to when we are when we're looking at a soils test, because as we know, as what we learned from Mark and what you learned from me in the plant nutrition classes, soil is the driver of nutrient availability. Buffer pH is basically that soil's ability to resist change of pH. That's very helpful when it comes to making recommendations on changing the pH of your soil, whether you want to acidify it or whether you want to increase the pH by adding lime. All right. Of course, I outlined the macronutrients that are done and the micronutrients that are typically done in a soil test. In the upper right, you see the cation exchange capacity, which something, of course, the Mark had talked about. I speak of during my plant nutrition program. It's just an indication of soil fertility and the exchangeable cations in a soil making it available for plant availability. Percent saturation is basically the macronutrients, the base cations that are on those exchange sites that Mark had shown you in that in some of his diagrams. So those exchange sites that are negatively charged exchange sites will hold cations, the positively charged ions, these nutrients. So you got potassium, calcium, magnesium, hydrogen, and sodium that are typically being measured on a percent base saturation. And this gives you just the knowledge of what the percent of these nutrients and other elements are on those exchange sites, okay? Not including the micronutrients. These are just in a percent-wise which elements are on those exchange sites, okay? And then from there you get different ratios of nutrients. Oftentimes when you are looking at changing the pH of a soil, especially if you're increasing the pH, you need to know what sort of lime to use. I talk about dolomitic lime and calcitic lime. So understanding these values here, so calcium and magnesium will tell you, you know, which lime should I be using, on top of the different ratios of nutrients in there, because the ratios are important when it comes to nutrient interference. So if you've got too much of one nutrient, it may cause problems with the availability of another nutrient. Okay. Now, looking at this, I'm sure you all recall that Mark had the same slide and the same graphic in his presentation. And I do like this graphic because it kind of gives you the idea of what pH is in the soils, and how pH is the master variable when it comes to nutrient availability, because it controls the solubility of a nutrient. It controls how these nutrients are made available to the plant roots. Now, these nutrients may be available in the soil, but if the pH isn't right for those, they might not be available for the plant to take up. And so Mark had talked about optimal availability of pH, which is between 6.5 and 6.8 for most plants. Now, if you're growing azaleas, pieris, blueberries, pH of 6.5 will definitely put these plants into deficiencies of micronutrients, because these plants have been adapted to acid soils, and they need to have more acidic soils. They're not efficient in gathering these micronutrients, so they exist in soils that have those micronutrients readily available for them. And that's certainly in pHs less than 5. The most micronutrients are more available in acid soils, as I said, and alkaline soils can tie up these micronutrients. So at a pH of less than 5, you're going to have soluble aluminum, which isn't a nutrient, but it's a very important element in soils. Iron and manganese at these levels of less than pH of 5. These nutrients, iron, manganese, aluminum, zinc, copper, boron, they may become toxic depending on their presence in the soil. on top of that, calcium and magnesium are less available in acidic soils, and phosphorus can be bound to aluminum iron. So in acidic soils, you might have phosphorus deficiencies. You might have plenty of phosphorus in the soil, but it's all being bound to aluminum and iron and unavailable. And in pHs above 7, your micronutrients are less available, and phosphorus can become bound to calcium and become unavailable again. So phosphorus actually has a very limited range of availability in soils. And so it's really important to understand, how this pH may affect the nutrient availability. And when you see problems in the landscape, and you see chlorosis or odd coloring in leaves, most likely it has to do with the soil pH. So when you have low pH, you're going to have deficiencies with phosphorus, calcium, magnesium, molybdenum, sulfur, potassium, and nitrate, nitrogen. And in high pH, you'll have deficiencies with phosphorus, iron, manganese, zinc, copper, boron, and ammonium nitrogen. And now, ammonium nitrogen and nitrate nitrogen are both forms of nitrogen that plants utilize. Most plants use both forms, but azaleas, Pieris, the heath plants or Ericaceous species, really use ammonium nitrogen. That's another reason why these plants particularly like to be in acidic soils. So these are the types of nutrients, these are the problems that these are the pHs and the nutrients that may problems with nutrients that may occur in these different pHs. Now, when we talk about leaf tissue and we're looking at the plants themselves, you can do a partial diagnosis of problems depending on where that deficiency is located on the plant. So if you have a deficiency in young leaf tissue, you are looking at deficiencies in what we call non-mobile nutrients in plant tissue. So those non-mobile nutrients are nutrients that once they are assimilated and put into tissue, they stay where they're at. They don't move. And so when a plant becomes deficient in that tissue or in that particular nutrient, it'll show up on the youngest leaves because the plant can't access or move nutrients from older leaves to newer leaves. On the other hand, older leaf tissue, nutrient deficiencies in older leaf tissue probably means that it's a mobile nutrient in that plant tissue. And those nutrients like nitrogen, phosphorus, potassium, and magnesium are being moved to the younger tissue where they're needed for growth. And so this is kind of like the key to kind of start you off in the direction of what nutrients you might be having problems with. When you are taking your leaf tissues, as I said before, the most recently matured leaves are the most accurate leaf for analysis. So let's get into some of the typical deficiencies I see in the environment or in the landscaping. So let's talk about nitrogen first. And the symptoms of the nitrogen deficiency and its causes. So the deficiency, as you've seen in that previous slide, occurs in the oldest leaves first. Why? Because nitrogen can be transported from these older leaves up into newer leaves for newer growth. You're going to get stunted growth, yellowing, chlorotic look to leaves. When it gets serious, you'll get leaf drop, especially those leaves that lost all their nitrogen. When the plant moved all that nitrogen out of those leaves become pretty much useless, and they will fall off. They'll senesce. You'll get an increased root shoot ratio. Not that you're going to start digging plants up, but what happens is when you get deficiencies of nutrients, your roots are going to be signaled to grow and explore the soil to find more nutrients. So root growth can actually occur better root growth can occur when you have less nutrients in the soil. And this is kind of one of those reasons why when you put new plants in a landscape, you don't fertilize them. You give them water, but you don't fertilize them, because if the fertilizer is already there, the roots are going to not want to tend to explore the soil. And the whole point of establishing a plant in a landscape is to get those roots to explore the soil. So don't fertilize. And you can utilize this deficiency for good and when you're starting off with new plantings. So what's the cause of nitrogen, low nitrogen availability? Well, just because nitrogen may not be available in the soil to begin with. You may have a organically deplete soil. You might have a soil that has a tendency to be waterlogged. Which when you have waterlogged soils, you'll have a lot of denitrification. Bacteria will start using nitrogen in anoxic conditions, which will actually deplete the soil of nitrogen. More often, the case is that you have a lot of carbon, or we should say cellulose in the soil. So if you have a soil that has a lot of cellulose material, let's say someone took mulch and had tilled it into the soil, and then you put a plant in that soil, that cellulose is going to create a nitrogen deficiency because the bacteria that are going to eat that cellulose for energy are going to use nitrogen to do it. And nitrogen will become deficient in the soil because of that cellulose. So you have to be really careful about the quality of the organic material that you add to your soils and your gardens and your landscaping, because if it's not well composted, if you still have a lot of cellulose in that organic material, you could end up with low nitrogen. You also can get interactions with potassium, calcium, and magnesium with nitrogen too. And depending on the soil pH, the type of nitrogen available will be a big issue. So in higher pH soils, azaleas may become slightly nutrient deficient or nitrogen deficient because they don't have the right nitrogen. They don't have the ammonium nitrogen, which is what they use in their metabolism. So what's the solution? Well, if necessary, you can adjust the pH and then use an appropriate nitrogen form to fertilize your plants, whether it's an organic form, which will have both nitrate and ammonium sources in. Mostly, if an organic form of material, it's an ammonium form. But if you've got a healthy soil, that bacteria will convert that ammonium to nitrate, and so both of those new forms of nitrogen will be available. And that's a close-up picture of a typical nitrogen deficiency in azalea. All right, let's talk about phosphorus. Phosphorus deficiency is an interesting one. It may not be due to the lack of phosphorus in the soil, of course, as I said before. It occurs in the oldest leaves first because phosphorus is readily mobile and moved to younger leaves. Older leaves, they darken and they turn purple, just like what's being shown on this slide here. The cause is either low phosphorus availability, meaning that it could be there, it could be not in the soil. Low pH, you'll have interactions with aluminum iron. You'll bind that phosphorus up and it won't be available to the plants. So you'll have interactions with calcium at high pH. So one of the main problems with soil or with phosphorus availability is just adjusting the pH to around 6.5. And you want to apply the correct phosphorus based on your soils test. What you don't ever want to do is apply more phosphorus to a landscape than you need to. So that soil test will give you an idea of how much phosphorus to apply. As we know, phosphorus is one of those nutrients like nitrogen that are highly regulated in Maryland because of our nutrient management laws. And certainly we want to keep those nutrients away from our waterways and that will go into the Chesapeake Bay. And here's some pictures of some phosphorus deficiency that you might see in the summertime when you've got in the middle of the growing season. Okay, let's step into one of the most common nutrient deficiencies I see in the landscape, and that's iron deficiency. So iron deficiency is primarily seen in the youngest leaves first, because when iron is assimilated, it's put into parts of the plant that it's just not mobile. So if the plant can't move it, and then those new leaves are going to show the iron deficiency first. And what you'll see is this very interesting interveinal chlorosis. So everything in between the veins turns yellow, and the veins themselves are rather green. And so it's this interveinal chlorosis, which indicates iron deficiency, but there's other micronutrients like manganese that can look the same. But in all, it's all due to the same typical problem, which we'll talk about in a little bit. The cause is low soil iron concentrations, which could be, but more likely it's high pH. And you'll have interesting interactions with manganese or with phosphorus, depending on if you've got really high manganese in the soil or really high phosphorus in the soil. You may have deficiencies in iron in the plant because the iron isn't available for uptake. Similar to high pHs. So any one of those interactions could cause iron deficiencies too, along with either the concentration of the nutrient not being there, or just the fact that the pH isn't right. So typically, to fix iron problems, it's just you adjust the soil pH, which is you need to lower the pH of that soil. And typically in a mature landscape, that can be done in a variety of different ways. You can use iron sulfate, which you need to be a little careful of, because iron sulfate is a very active acidifier of soils. And so that's one possible way to lower the pH of a soil in an immature landscape. You can use certain types of nitrogen fertilizer, ammonium-based fertilizers that are acidic and acidify the soil, are typically what's used. And when you're growing blueberries, you use ammonium sulfate for your nitrogen source, not anything with nitrate in them, but you use ammonium sulfate. And that's similar to iron sulfate, lowers the pH of the soil. You can apply a chelate. And a lot of times, and what a chelate is, it's basically a compound that contains that micronutrient in that compound, and it can be dissolved in water and sprayed on the surface of the soil or on the leaf itself, and the plants will absorb that particular micronutrient. And so there are iron chelates out there. The problem with chelates is they're very expensive. And they don't necessarily solve the problem. They only put a Band-Aid on it. And the real problem is actually the soil. And here are some pictures of typical pictures of, looks like I had an animation problem in there, but that was just another tree, an oak tree that was showing iron deficiency. So apart from iron deficiency, we can get into magnesium deficiencies. Magnesium deficiencies kind of look like iron deficiencies, but they're really throughout the whole plant, and they occur in older leaves also. There's interveinal chlorosis, which is like that. You'll see it in spruce trees, in a variety of different trees with very similar symptoms. It's again interveinal chlorosis. It's due to low soil pH or low magnesium concentrations in the soil itself. And with magnesium, you're going to have interactions with high calcium concentrations. So again, this is where the soils test really helps you out to figure out what's going on, because you might have magnesium in the soil, but if you have a preponderance of calcium in the soil, you're going to have interactions with those nutrients and they'll compete for root uptake. So calcium can interfere with magnesium uptake. And so you have to make sure that in the landscape, when you're doing your soils test, and when you are developing a new landscape, you make sure that your calcium and magnesium concentrations are both moderate or at an optimal level. This is a typical soil analysis report. This is the one that I give you on in the plant nutrition lecture for trainees. The percent base saturation, again, it's one of those things that used to be used to determine whether, to determine where nutrients are and what was available. They used to determine a long time ago, they would look at the percent base saturation ratio of magnesium and calcium. And if it was above 7-to-1 calcium magnesium, then the recommendation was apply magnesium. And if it was below 3-to-1, meaning there was a lot more magnesium than was needed, they would say apply calcium. The base saturation isn't really used anymore. Really, they're just focused on looking at the actual levels of the calcium in the soil itself. So in this case, you got 75 parts per million calcium. It's low for the plant. And you've got 1,291 parts per million. That's a really big difference in calcium and magnesium rates. So if I needed to increase the soil pH, I would be using a dolomitic lime. So you would adjust the soil pH with dolomitic lime if the soil pH needed to be adjusted. But if the soil pH didn't need to be adjusted, you could apply Epsom salts. And that would give you the correct magnesium. That would give you actually magnesium, but it would not correct your pH, which is already okay. Let's talk a little bit about potassium. Potassium occurs in the oldest leaves first, primarily because it is it's mobile. All right, the next highest concentrations of nutrients next to nitrogen in a plant is potassium. Potassium is a nutrient that there's a lot of it in plants, and most of the time potassium is being taken up with nitrogen. What you'll get is marginal chlorosis and then leaf death. What's interesting is it mimics drought stress. So sometimes you might see leaves that have this marginal chlorosis on them, and you'd think, well, could it be potassium? Well, it might be just drought stress. Which is actually, you see that more often than you see potassium deficiencies. The cause is either low soil concentrations of potassium, or you may have, again, interactions with calcium and magnesium. If you have really high values of calcium or magnesium in the soil, you might have interactions which make potassium difficult for plants to take up. A low pH and low uptake of nitrate will also cause potassium deficiencies. And so oftentimes, nitrate and potassium oftentimes work together when being taken up by the plant. And so typically with when plants are taking up nitrate, they're taking up potassium. So potassium nitrate is one of those ideal nutrient sources for plants if you're using chemical nutrients. And the solution is to add potassium. And that can be done a variety of different ways. And then when fertilizing, if you're chemically fertilizing, you definitely want to use a nitrate form of fertilizer because that aids in potassium uptake. Let's talk a little bit about toxicities now, because essential nutrients can also be toxic. They can either be toxic directly or indirectly. And I had kind of alluded to a few of those indirect toxicities. But let's talk about some of those direct toxicities first. Well, actually, this is a chart that talks about or that kind of informs you on indirect toxicities. So if you have an excess in one of these nutrients in the column to the left, you may have a deficiency in plant tissue of the nutrients in the right side, the right column. One I like pointing out is the phosphorus, so if you're over applying phosphorus, you might have problems with iron deficiencies in your plant. So you're making sure that you're balancing your nutrients, that when you have when you're applying nutrients to a soil, you want to make sure that you're not over applying any particular nutrient. And this is where kind of compost comes into that factor, where it's always a good idea that if you're very serious about your garden and very serious about your landscaping, that you know exactly what's in your compost before you're applying it. And on top of that, having a soils test to determine what you're applying is okay. Because the soils test will tell you what's in the soil, and certainly that compost test will tell you what's in the compost. Keep in mind that a compost test, all right, and a compost analysis is not a soils analysis. They use a completely different method. So when you send in a compost for analysis to a laboratory, it's important that you tell them that it's a compost, because they're going to perform a different test. If a soils test is performed on a compost, it'll give you erroneous information. And you really need to understand that. So it's important. And on top of that, if you have a soil that's 50% by volume organic material, you probably should get a compost test done because of the magnitude of compost. And it's not necessarily 50% organic material by weight, which is what the loss on ignition does, but it's by volume. So you want to be real careful about which soils test you use. In most cases, we are not growing in soils that have 50% compost by volume or weight. All right, so it's not something that I would worry about. It's just something that certainly, if when I work with my nursery and greenhouse growers, and they do a soils test, or they're doing a substrate test, they're using a compost style test, because the material that they're working with, the material that they're growing their plants in, is actually an organic material. So manganese is one of those that I've seen in the past. The toxicity varies among species. Different plants are more sensitive to manganese toxicity. Those Ericaceae species, the species that live in acidic soils, aren't susceptible to the manganese as much as plants that live in higher pHs. You'll get dark purple or brown spots in the leaf margins, and you get this leaf tip necrosis. This is actually, with this geranium, looks a lot like iron toxicity too. And so manganese and iron toxicity both arise from probably the same problem. You have very low pH, soil pH, which increases your manganese availability and iron availability. In soils, it's typically manganese. In substrates, it's typically iron toxicity that we work with, that we see, and especially when it comes to growing geraniums. Waterlogging might be the case, where you have a completely saturated soil, and you'll have an anoxic condition, which creates an acidic environment, which those nutrients can become very available and very toxic to plants. And the solution is basically to increase the soil pH. And that's how you would, and so you'll need a soils test to manage that, and to understand how much lime to use on that soil. We've also used silicon. Certain silicon based compounds can be very effective in reducing the symptoms of manganese toxicity and iron toxicity, primarily because silicon compounds have a high pH to them, and it just raises the soil pH. Phosphorus toxicity, it's basically it's an iron deficiency. You get interveinal chlorosis on youngest leaves, and it's because of high phosphorus soils. Whether that high phosphorus came from management, organic materials that were put in that landscape previous, or maybe a phosphorus fertilizer was used to too much of it, but it binds to, but the phosphorus binds to the iron. And it creates this iron deficiency. And iron deficiencies, and you'll also have this low pH situation because the iron and the phosphorus are binding together. And the solution to phosphorus toxicity is just to adjust the soil pH and apply iron chelates to bring up that iron concentration. Additional toxicities: sodium, chloride, fluoride. These are all halide. The chloride and the fluoride toxicities often derive from the type of irrigation water we have. Sodium certainly comes from road salts. So when we talk about road salt injury, we're talking about plants that are damaged from road salt or from the sodium chloride that's being applied. It resembles drought stress and creates root damage. You'll get foliar browning, marginal necrosis, branch tip or stunting or dieback. It's sometimes confined to one side of a plant and can occur, and typically because that's where the salt's being applied. Sometimes there's splashing of that salt material onto the tissue, and it can occur within 50 feet of a road. So it's just one of those things where these road salt injuries it can be pretty widespread. I've seen a lot of it on my travels. And even species that are tolerant of road salt can have problems. And drought-stressed plants are more prone to injury. Some are more tolerant of salt than other plants are, but in general, you really have to manage the sodium. You want to wash off that foliage. You want to create or avoid creating or minimize the snow piles that we make in driveways or such, because if we're applying salt and we're piling snow piles up, we're making snow piles, we're concentrating those salts. You want to leach the salts out of the soil, and basically you do that with irrigation. You can also amend soils either through organic material, activated charcoal. One of the most useful materials is gypsum, which is a calcium sulfate. None of the above are quick fixes. I know that one landscaper who often works with gypsum applies it in the fall and actually uses it as a preventative. Gypsum sodium has a tendency to disperse soil particles, so they get mucky. The use of gypsum creates a competition on the cation exchange columns, okay, the cation exchange sites, and calcium will bump the sodium off of the exchange sites and allow that sodium to leach down through the soil with either irrigation or rain. The sulfate in the gypsum competes with chloride and combines with the sodium so that all of that can be leached through the soil profile much more easily. Your gypsum rate is dependent upon the salinity or the sodium absorption ratio, which is just a complicated, which we're not going to get into, but it's just a mathematical formula of sodium availability on the exchange sites. And typically with gypsum, they're using between 10 to 50 pounds of gypsum per 100 square feet to manage soil, to manage a sodium chloride. I thought that was rather interesting. That is a lot of gypsum. So let's talk about water and what you see when it comes to water stress. You typically get stunted leaf growth. So when you see a plant in water stress, the leaves are going to be much more smaller than normal because it's water that expands the cellular tissue. And when leaves are small, they're typically an indication of water stress. Your internodes, the spaces between the branches become very short. And oftentimes you'll get this leaf tip scorch, which can mimic potassium deficiency. Low soil water availability is the cause, poor soil quality, compaction, poor drainage, or it might be that your soil is just fine, but your roots are dying for some reason or another, whether it's disease, poor management, something happened to those roots at some point that would have caused them to die back. And if you don't have roots, you're not going to have water uptake. The solution could be irrigation or solving a root problem, figuring out whether you have disease or nutrient toxicities, which are killing your roots. Okay. All right. So to end this up, in summary, we really want to take a systems approach to diagnosis for landscape nutrient deficiencies. You have a toolkit. You use that, you have, you know, the things that I talked about today. You ask questions to the landscape owners, you do soil and leaf analysis, and pretty much you can hone in on problems that may be nutrient related. Understand the difference between abiotic and biotic issues that may show similar symptoms. Many nutrients exhibit similar deficiency symptoms, so sometimes trying to hone in on one particular nutrient is difficult, because oftentimes your deficiency symptoms show up the same with different nutrients. And of course, different plants may exhibit different symptoms, which can be really tough in the landscape industry. One plant may not exhibit the same symptoms of nitrogen deficiency or phosphorus deficiency as another plant. And some issues may have been caused by past events. Certainly, the types of amendments that are being used, the management of the landscape, or even to the point where how well was that, what care was taken when that plant was put into the ground. Okay, that ends my my talk, and I'll be happy to entertain any questions up until the point where we have no time. I know that I've got a lot of questions to get through today.
That's so true. Thank you so much, Andrew. Such an informative lecture. I really appreciate it. I'll get
Absolutely.
right to those questions. Insecticides like Mosquito Joe, could they cause chemical damage and or stress to the plants?
Typically insecticides don't, but could, and it really comes down to the chemical and what's on the label. So obviously, you never apply any pesticide, whether it's a fungicide or a pesticide, to a plant that's not labeled. So labeling is extremely important. And if it is labeled for the plant you're using it on and the target organism you're using it for, you typically will not have any chemical damage. However, I've seen firsthand when you spray wasp spray on plants because you're trying to kill a wasp nest in one of your landscape plants that you're afraid you're going to get bitten, that wasp spray will kill leaves. And you will get damage. So it just depends, and it may not be the chemical itself, the active ingredient. It could be all the other inert components that create that wasp spray that do it. So it just depends on what that chemical is and how that chemical is labeled for the application that's being used.
Thank you. Regarding soil testing, can you recommend where to send soil and or compost? I know they're two separate tests. Where to send them for testing? I don't think university does the soil testing anymore. Is that
Not
correct?
anymore. No, we got
Yeah.
we had to stop testing because it was a huge financial drain, and it occurred during that terrible recession that we had in the about 12 or 13 years ago. So we did get rid of our but that doesn't, there are plenty of places, Penn State laboratories, there's AgriLabs in Harrington, Delaware, there's the University of Delaware, there's lots of different places that you can send to. And if you're really curious, you're more than happy, I'd be more than happy to send you an information sheet on all the different soil laboratories that can do a compost analysis and a soils test and a leaf analysis. Just send me an email and I'll send you that information.
Wonderful. Thank you for that. And what about an app? Can you suggest an app that IDs plant diseases? I know Picture This is a great one, but it isn't detailed enough in terms of plant disease.
No, and I don't think I can offhand because oftentimes, because you've got so many different diseases out there and so many different cultivars of plants and varieties and species, all exhibiting different symptoms. I don't think I've not heard of an app that can actually, if you could take a picture of a plant leaf and it'll tell you what exactly is wrong with it, or give you a list of different things that are wrong with it. It's really about sleuthing at this stage. Again, if you can find an app that does that, that'd be amazing. I'm sure with the AI that we have, something is going to be developed eventually. But it's really about sleuthing. It's about looking in the internet. It's about getting onto a lot of the land grant systems extension sites throughout the United States, who have fantastic fact sheets And it's just about doing your own research on these and to learn and developing a book in your mind on what you see in plants. So no, there's no app, but there's all kinds of things on the internet. And be careful, because the internet oftentimes gives misleading information. Sometimes that information is not correct, but it may lead you down to a few different ideas, which you can then hash out if you need to do a soils test or a leaf test.
Fair enough. If we ever find one of those apps, we'll be sure to email it to
You tell me, exactly. I'll test it out.
Oh, perfect. So can you please explain what soil conductivity indicates?
Yes, I didn't. I noticed that. Conductivity is just merely merely how well electricity is conducted from one point to another in a soil solution. So basically, it's electrical conductivity. I called it EC, which is electrical conductivity, and it indicates the amount of minerals in the soil solution that can conduct electricity from one point to another. And so that electrical conductivity is a number, and I won't get into the details of that unless you're really super interested, but it just tells you how much salt is in the soil. Now, with soils, because of what Mark had talked about earlier, when you have very reactive clay particles that have negative charges and minerals and nutrients, soil pH is much more, or soil electrical conductivity is much more difficult to interpret than when we're just working with soilless substrates. Those things like the peat moss and pine bark that we're growing our plants in containers, because those organic materials are very inert. And so when I talk about electrical conductivity to my growers, they use that to determine whether there's a salt load in their containers and whether they need to irrigate or not, because salt can kill roots. So when I talk about electrical conductivity, typically I'm referring to electrical conductivity in soilless substrates or potting substrates, potting soil, which soil is not typically I use with potting, but nonetheless, it's a measurement of salts in a soil solution. Okay.
That's great. And can you tell me if there is a difference between nutrient availability in potting versus garden soil, and also plastic versus ceramic?
Excellent question. Absolutely. And the reason why is because organic material is an organic, potting media is organic with some oftentimes inert minerals in them, or sometimes there's vermiculite in. And I haven't seen vermiculite in a potting media in a long time. But other than vermiculite, most of the things that they put in potting media is very inert, meaning there's just not chemically active. But because organic media has a relatively high cation exchange capacity compared to just a regular soil, because it's organic, your levels of pH or your levels of nutrient availability are very different in a potting media than in a soil, primarily because of the cation exchange capacity, the relatively high cation exchange capacity in a potting media, because it's organic. So there is a difference in availability when it comes to potting media. And primarily when we're working with potting media, we're throwing in fertilizers anyways, because that potting media doesn't have a lot of natural nutrients in it. So we could be throwing a little compost or fertilizer, which would actually increase the fertility of that potting media to begin with. So it's just the nature of the beast of potting media that kind of changes your whole view of how nutrients are available in those particular substrates.
Can you tell us, does the repeat application of hardwood mulch cause a toxic buildup of manganese, and is pine bark mulch better?
It depends on the source. It depends on where that, yes, because I've heard of this before, and especially with pine bark, and certainly with hardwood. I've also heard that you can get into manganese toxicities if your soil goes acidic on you. The problem is that you never know, because manganese being taken up by the plant you know, the trees where these, or in the pine trees where these plants are derived from, you know, it depends on the availability of those nutrients in the soil where these plants are growing. So in one location, you might have trees that are being harvested for mulch, and there might be high concentrations of manganese in those soils, which may not necessarily be detrimental to the plants when they're growing, but because bark and cellulose are storage tissues, that material, those nutrients can build up quite a bit. And especially when you then compost those materials, you're actually taking a large volume and compressing it down to a small volume. Those salts are still there. Those nutrients are still there. So you never know when you might have a problem with manganese toxicity or iron toxicity. It happens often in container production when we're growing in these types of substrates. And if that's why these growers have to manage their pH very carefully. But typically in a landscaping situation, in open soil, these things don't occur. They do, but it's not often.
Fair enough. And even testing the mulch wouldn't even make a difference. It just depends on the soil that it's in.
No, because really you can test the mulch, but you know, it's one of those things where unless they actually digest the mulch, where you take that organic material, just flushing water through it to see what's available, it might not tell you what's in that mulch, because those nutrients are actually assimilated into the organic material of that mulch itself. Again, it's unlikely that these things can occur, but it has happened. I know I know I've seen it before, but it's very rare.
Understood. Can you tell us how can a gardener evaluate if the cash and exchange capacity is good or poor?
All right, so that's a good question. What this person is looking for a value to know whether their cation exchange capacity is doing well or not. A lot of it has to do with, you know, so cation exchange capacity is one of the indicators of fertility, not the indicator of fertility, but one of the indicators of fertility. So you might have a low cation exchange capacity, but you might have a good nutrient source. Your soil might be relatively fertile in other ways. I would say that if your cation exchange capacity is around 10 or higher, you're doing really well. Another aspect is looking at your organic content. There was an organic, in a soils test, there is organic material. It's an OM test. And depending on how much organic material and how well that organic material has been disseminated and has been degraded, that could also be an interesting indicator. A lot of organic material, if you notice, remember Mark's pie chart, some of that organic material is in the form of humus. Some of that organic material is in the form of residuals that have not been broken down yet. But that organic material test isn't going to tell you that in the soils test. It's gonna burn up everything organic, and it's going to give you an estimate of what's available there. But if you have a garden and you know you're putting organic material in, compost, things that you create from your own yard or from your own kitchen waste, and you're putting that in there, and you have an organic test that way, then you know pretty much that organic level. If it's above 3%, you're in good shape. Most of our soils in Maryland, agricultural soils, are below 3%. But 2 or 3% is not 3% is not bad. Higher than that, you're going to get into a lot higher fertility and cation exchange capacity.
Understood. Thank you. I think I have one last one before we got to take a break here.
Yep.
And that's at what pH do we start to see iron uptake deficiencies in the soil?
Iron uptake of deficiency. So so typically when you start getting, and this is again by plant, because some plants are able to pull iron out of the soil better than others. Okay, so typically we're looking at pHs of around 7 or higher is when you start seeing quite dramatic iron deficiencies. So 7 or higher is when you see iron deficiencies, and below 6.8, 6.5, depending on if there's iron in the soil, and in Maryland there typically is, you probably won't have a problem.
Thank you, Andrew. Now, there were a few questions still left over. Can people email you directly at that
Sure.
address you have?
Yeah, no problem.
Well, I want to thank you again for this really well-organized, informative lecture. And there's been a lot of great comments in the chat box. And we appreciate your time.
And if you wouldn't mind giving me an evaluation for today's lecture, I would very much appreciate it. It helps me develop my programs. It helps me get better at programming. So please, as many people as can, you can either use that link, which is the goumd.edu ag teach. There's the information on how to do it. Choose the presenter, choose the date, choose the nutrient, choose nutrient. Actually, since this is Master Gardeners, you have to choose another, I think it's natural resources. So I apologize. This is not the correct evaluation link to give you. I made a mistake. So what I'm going to do is I'm going to get, if I can, Ryan, can I send you the link to those that you could distribute out to your Master Gardeners?
Absolutely. I'll take
Oh, I
care.
appreciate it. Thank you so much. And I apologize for this. I would definitely like an evaluation. Email me, everyone, and everyone have a wonderful day.
Thanks so much, Andrew. You as well, please.
All right. Bye-bye.
Thank you. Bye. All right, so that'll give us about 7 minutes to stand up, stretch out, take a quick coffee break, and then return for our final speaker, Chris Piat, and he'll be talking about PFAs in the soil. Thanks so much. All right, welcome back. See, Chris has his presentation all ready to go, and I'd like to introduce him. Chris Piat is the Director of Resource Recovery for the District of Columbia Water and Sewer Authority, DC Water. He directs the recovery of resources at the authority by establishing policies, plans, and procedures related to the recycling and extraction of value from recovered resources. Chris also works to optimize the reuse of all the authority's underutilized resources, including the biosolids program. Chris has a BS in Civil and Environmental Engineering from the University of Wisconsin-Madison, and an MS in Civil Engineering from California State University at Long Beach. He's also a licensed professional engineer. Welcome, Chris.
Thanks. I really appreciate the opportunity to come talk about this a little bit. Yeah, I'm the Director of Resource Recovery at DC Water. I love my job because it's my job to turn over rocks and try and find opportunities that are underutilized. And that includes energy in the wastewater. We've got a bunch of energy projects we're working on, but also the recovery of the nutrients and the carbon in our biosolids. This front cover slide is my home. This is the Blue Plains Advanced Resource Recovery Facility. It was built in the 1930s when all we did was slow the flow down and settle out solid material and then pump water, clean water, I'm going to use air quotes, clean water out into the river. You know, but that wasn't enough. We weren't taking the carbon out. We weren't taking the nutrients out. So it's our job to remove those, the carbon and nutrients, so they don't end up in the Potomac River and then ultimately out in the Chesapeake Bay, because we don't want to upset that very delicate balance. We all recognize that's a resource well worth preserving. But carbon is energy and nutrients are fertilizers. So we wanted to build a system that not only captures all of this, but is able to optimize it, and so that we can make use of it. You know, if a bear comes out of the river or comes out of the woods and goes down to the river and scoops up a salmon and then eats the salmon and then comes back into the forest and poops on the forest floor, soil microbes attack that pile of bear poop and convert that organic nitrogen into plant available inorganic nitrogen and make more soil. And, you know, I think sometimes we humans forget that we're part of the ecosystem. So it really makes me cry if I go to a city and they're taking their biosolids and they're landfilling it and locking it in the landfill. And no other animal on the planet would do that. So we have systems to capture the carbon. It is, I don't know if you can see my cursor here, but these tanks up here on top, brownish tanks, are activated sludge tanks, and it is a system by which our water that goes through the primary tank settles out organic matter, still has a lot of dissolved carbon in it, and it still has a lot of nitrogen in it. It goes through that system, and it's a microbial process where it's the microbe's job to consume the dissolved carbon, and it's about an 8-hour process. So by the time it gets to the end, we have fed a lot of food into that system, the food being the wastewater, and they've removed a lot of the carbon. And by the time they get to the end, they're just these microbes that are sort of like water balloons filled with carbon. And when we settle those out, and that's one of the sources of solids that go over to our digesters to make methane. Then the water that has the carbon out of it still has a lot of nitrogen in it. It goes to these tanks over here. This is our advanced nutrient removal process. So again, it's a biological process. It's a 2-stage process that goes from organic nitrogen to nitrite to nitrate to nitrogen gas. And it blows it off into the atmosphere, which is fine because the atmosphere is 78% nitrogen. And then the water comes over to these settling tanks, and we settle that out. And most of the microbes go over to the digesters. That's the next source of solids for the digesters. The lucky ones, I guess, depending on your perspective, get to go back to the process to maintain that population. So we're continuously reseeding both the biological nutrient removal process and the carbon removal activated sludge process. So then the unlucky ones, I guess, again, depending on your perspective, get sent to our digesters for conversion into methane and into fertilizer. This is not advancing for some reason. That is odd.
Do you want us to take over on this end, Ann?
Oh, I got it.
Oh, there it is.
Figured it out. Thanks. So we have, we're very, very proud of the fact that we're completing this carbon and nutrient cycle. The agricultural areas produce food, or they get flown in from other areas, and we process that food through our bodies, and we send it down to Blue Plains, which is where I work. And we clean it up. We put clean water back into the river. And if I can go back to the last slide just for a second here, this is our discharge point, and it looks like an inky black spot, but it is the cleanest spot on the river. It's clear. The Potomac's pretty muddy, and it's clear, way cleaner than the water that we take out at Great Falls to turn into drinking water just to send to the citizens of DC and our ratepayers. So we're very proud of the work that we do and returning carbon to the or returning clean water back out of the river. And then concerning the carbon and nutrients, we send a lot of it out to agriculture. We have relationships with farmers where we send it back to the farms. But we've recently put in digesters to give us a higher quality product. EPA has several different sort of levels of treatment, and you can do different things with them. If you meet Class A exceptional quality standards, which means a complete obliteration of all the pathogens, and it's very stable, it's low odors, you can use it in an urban setting, you can sell it to the public. So because we did that, we've been able to tighten this circle and use a lot of it within DC. I don't know if you've been over the new-ish Frederick Douglass Bridge right by the Nats Stadium, but all of that landscaping on the other side of the Anacostia, on the east side of the Anacostia, it was all done with bloom. We did 8,000 yards of bloom over there, and it's just beautiful. It's really nice because I tell my colleagues at other agencies, and they say, "You use that right in the middle of the city?" And I say, "Yeah, we did. It worked really well because we chose every piece of equipment with product quality in mind." We wanted, and I don't think that this has ever been done at a wastewater treatment plant with, certainly not of our scale. We wanted to maximize the product quality of 4 different things. One, of course, the biosolids coming out of the bottom. One, the gas coming out of the top. Another, the electricity that we can make. We wanted to make some power. and then the heat we could recover. So the way that this system works, and the magic is these silver cylinders in the middle, that is thermal hydrolysis process. This happened to be a Mcmg system. It's a Norwegian technology, and it's the first one in North America, the largest one in the world. It's all over Europe, though. They've been doing this in Europe for 20 years. So we went and vetted the technology, and really it's like a pressure cooker, high heat, high temperature, high pressure, high-ish pressure. And this first tank is where we add the steam, and we heat it up to 160 degrees centigrade, not Fahrenheit, but centigrade. And then these tanks in here hold it for 20 minutes. So it's 160 C for 20 minutes. That's well above pasteurization. Pasteurization is 70 C for 30 minutes. This is 160 C for 20 minutes. And then it's also under high-ish pressures, high by our standards. You know, we're sitting here at about 14.5 pounds per square inch. That's atmospheric pressure. We have this under about a 90 PSI, which is about 6 times atmospheric pressure. And then it goes to the last tank over here. The last silver tank is slightly larger. And that is, it's called the flash tank, and that's back at atmospheric pressure. And when the material goes in there, that sudden pressure drop causes the cells to burst. And I mentioned earlier that our secondary process ends up with these little water balloons filled with carbon. That releases all of that carbon and makes it much more available for the hungry microbes in the digesters. The digesters are filled with archaea. We have archaea in our gut. It's part of, you know, it's a naturally occurring, it's not a bacteria, it's its own family. But it's archaea's job in nature to convert organic matter to methane. So we optimize the conditions for the archaea. So we get a lot of gas production because we've released that carbon from those water balloons. And then as a result, we get a very stable product coming out of the bottom, because most of what can be converted to methane has been, and it's only really the conversion resistant material that comes out of the bottom. And that's very stable, which means it's very low odor. So we had all these different criteria for how we wanted to choose equipment, and odors was one. Even though it's not regulated, it's still our biggest issue, and certainly it's a product quality issue. We knew that we needed to have consistency in order to convince the public to buy a product made from human waste. It's a lot of hard wiring in our brains to avoid human waste. So it had to be consistent. It had to be low odors. What triggers the fear with human waste, of course, is the odors. And so we wanted it to be low odors. So then, you know, the gas comes out of the top. We clean the gas up in a building back here. It takes out the sulfur compounds and a couple other things, some of the CO2. It cleans it up so that we can send it to this building, which has 3 5-megawatt turbines. We feed the gas into the turbines. They use it as a fuel. It spins, and we capture that motion and create electricity. We create about 8 megawatts of power, which we use on site. It's all behind the meter. We're the biggest user of electricity in DC. Our demand is about 25 megawatts. So we produce about a third of what we need, which is great. Saves us from buying the less environmentally friendly power off of the grid. This is considered to be a renewable energy source, so we get renewable energy credits for that as well. And then again, we wanted to optimize the energy system so that we could recover heat. We could have put an internal combustion engine in there and burnt the gas in an IC engine, but IC engines don't run as hot. And if we did that, we'd make maybe a couple 1.5 extra megawatts of power, but we would have had to have put a giant boiler right next to our cylinders here to burn natural gas to make the steam. That didn't make any sense to us. So when we looked at the energy balance, it made more sense to put in the less efficient turbines for electricity because they run hot. So at the end of each of the turbines, we have a heat recovery steam generator. We pull the heat off, we make steam, and that's how we heat this up to 160 C. So it's incredibly energy efficient. Super proud of that. So out of the bottom of the digester, we get this product, which we have branded as Bloom. It's really, I mean, I've seen thousands of biosolids products, and this is no hyperbole. It's the best one that I've ever seen, and it's largely because we chose all of this equipment to give us a high quality, low odor, consistent product. We have website, bloomsoil.com. It has all kinds of analysis on it. It has testimonials. It has research that we've done, growth trials. I encourage you all to check it out. It's being used all over the area. The architect of the Capitol has used it on the mall. They've used it around the cherry trees at the tidal basin. Very proud of that. The bottom left one is a construction project that was done by Lane Construction. This is a section of Route 5 in Maryland, just north of us, north and to the east of us. They ran into a problem because, you know, they did this big cloverleaf exchange, and then they had to get grass to grow, and the soil was so bad they couldn't get any grass to grow. And of course, you know, the customer was retaining some money until they grew some grass there, and they went to a composter and they got some compost and they blended it in with the soil and some sand, and they sent it into the state highway authority, and it met that spec. They said, great. So they put it down. They got about a third of the way through the project. They ran out. They went to the composter, and he said, "Oh, I'm out. You know, why don't you try this guy?" So they went over there, picked up some compost, blended it up, sent it into the SHA, State Highway Authority. It didn't meet the spec, so they were scrambling. And we said, "Hey, we've got a product for you. We've got this Bloom Biosolids, and it's incredibly consistent. You know, we're a big plant, so there's very, very, very little variability in what we produce." And at your scale, we have almost a limitless supply. So we said, why don't we blend some up? And they blended it up, and it, lo and behold, it met the State Highway Authority soil spec. And now they use that product almost exclusively. The one in the middle is Four Streams Golf Course in Montgomery County. Used a lot of our blends up there. And then on the right is a farm, soybean farm. Our customers are sort of a who's who of landscapers, soil blenders, construction firms throughout DC. It doesn't happen by accident. You know, we do demonstration projects. This picture up on top with the kids is a demonstration we did at a school, Tyler Elementary, to where all my kids played soccer, and they had this horrible field over there. Just couldn't get any grass to grow, and it was all rutted up. And so we donated some material, and we all went out and we spread it, and now they have this lush green grass. And it's, you know, a lot of word of mouth. We do tours. We bring people in. Anybody who wants to come, just let us know, and we'd be glad to give you a tour. We love showing off what we do. I always say, I think that, you know, when we talk about Bloom and it comes from human waste, they think that, you know, people just have this image in their mind of us just shoveling a bunch of turds into a truck. That's not it at all. There's so much technology and, you know, microbiology and physical processes and everything that goes into protecting the human health and the environment. So please do come for a tour. We grow all kinds of different things in Bloom. We have, you know, vineyards that do it. We grow hops, or we don't, but our customers do. Lots of school landscaping, flowers, hay farms, commercial corn. We've even done some wetland restorations. It works quite well for that. So the benefits are, you know, it's a great value to the farmers for the soil health, adding all that carbon, adding the beneficial microbes. Really, I mean, it helps when you add the beneficial microbes that come out of the digesters naturally occurring. It helps resist soil disease. You know, soil diseases thrive when conditions are bad and there's not enough organic matter there, and the good microbes can't outcompete. But when we do this, we allow the good microbes to outcompete the soil diseases. Really, it helps preserve agriculture. I heard somebody earlier talking about the fact that, you know, the farmers are under immense pressure economically, and as, you know, the development spreads out further from the DC area, the farmers are tempted to start growing McMansions and subdividing. And this, I think that this really helps with their economics, and it helps keep family farms running. Really, it completes that nutrient and carbon cycle. It reduces our carbon footprint. That one project that we did, the digester project, reduced our carbon footprint by over a third, and we're the biggest user of electricity in DC, so it was enormous. It reduced our carbon footprint by about 50,000 metric tons of CO2 equivalent emissions annually. Of course, it helps protect Chesapeake Bay by reducing the use of chemical fertilizers. These are all slow release fertilizers. And ultimately, it reduces costs for our ratepayers. So it's a financial win, it's an environmental win. Now, it's not all unicorns and rainbows. I get that. I just gave you the unicorn and rainbow version of biosolids. You know, there's everything that comes down the sewers ends up at the treatment plant, and some of it ends up in the biosolids. And today, I just want to talk to you about PFAS because I'm concerned about it too. You know, it's in my blood. I don't like the fact that it's in my blood. We all have a little bit of PFAS running through our veins because of all the products that we've used throughout our life. You know, I remember my mom having all those pans with non-stick coating, and it was miraculous because it was super easy to clean those eggs off the pan after we made breakfast, and I liked it. I did the dishes. But you know, we ingested some because of that, and eventually it started peeling off, of course. And so it's everywhere. It's in paper to make it stronger and to make it water and grease resistant. It's in plastic to make it stronger. It's in clothes to make them water resistant. I mean, I love my Gore-Tex jacket. I'm sure it probably has a coating of PFAS on it. It's not good. So it's everywhere. And it can have some at elevated levels. It's been shown to have some negative health effects. So, you know, we use all of these products, and a lot of the products end up in the trash. So paper and plastic waste goes either to a landfill or to an incinerator. And at the landfill, it ends up in the leachate because they have to collect the leachate. They can't just let that drain down to groundwater. Of course, nobody wants that. But then where does the leachate go? It comes back to the wastewater treatment plants for treatment. And it's just it's a vicious cycle. It continues to concentrate. Excuse me. Just need to get a drink of water. What we have seen, though, in our bloodstreams in Americans and other people is when the production of some of these things were banned a few years ago, we started to see a drop in the blood levels. So really, I mean, the solution is source control and not using these products and not getting them, you know, not allowing others to import them into our country. But it's everywhere. I just recently was at a conference. In fact, I flew back yesterday. It's our annual wastewater conference called WEFTEC. And somebody was saying that it has been found in toilet paper, which of course ends up in the toilet and ends up at the treatment plant. And you think about it, I mean, not to get too graphic, but you of course want your toilet paper to be reasonably strong, and it's probably in there for that purpose. And then, you know, trash also gets incinerated. Plastic things, all kinds of things end up at the incinerator, and it ends up in their exhaust, and then you have atmospheric deposition. It's not good either. And products and food waste, which can have PFAS in it because of the packaging, enters our sewers through the sinks and through laundry and through industry. In DC, we have very, very little industry. We only like 6% of our flow comes from industry. And we have a pre-treatment program that if they're discharging into our sewers, they have to have a permit. We impose limits on them, and we go out and we do sampling. And if we find that they're exceeding the limits of their permit, we can cap their sewers. So they take it very seriously, because if we cap their sewers, in many cases, they're out of business. And while the highest concentrations are from industrial sources, again, we don't have a lot of industry here. The greatest mass actually comes from residential areas. I saw a couple presentations at WEFTEC that showed a surprising result. You know, of course, everybody's thinking about industry and let's limit industry. But if you do a mass balance on what's coming into the plant, they did samples out of different sewers coming from residential areas and industrial areas. Yes, the highest concentrations came from in industry, but because of the enormous flow coming from residential areas, even if it was a much, much smaller concentration, it meant more mass coming in. So most of the mass is coming from our homes, from the products we use. So a few years ago, the Sierra Club did a study on a bunch of different products, one of which was our bagged cured bloom. And they did it surreptitiously. They went to a store and they got it and they peeled it open and they took a sample and everything. We would have gladly cooperated with them. But they did this, without our knowledge. It's fine. They got some results that were slightly higher than ours. Most of what we produce is what we call fresh bloom, and then we use the fresh bloom in blends. What they tested was our cured bloom, and they came up with the two compounds of concern are PFOA and PFOS, and they came up with about 23 and 22 for those. When we test, it consistently comes between 3 and 4 for PFOA, and about between 15 and 16 for PFOS. There's a couple explanations as to why that happens. It might be something that is happening when we cure it because we're using air. It also might be coming from the plastic bags. I think that's, I'm not really sure. In either case, the limits are below all these limits, even the ones that the Sierra Club tested for, are below the newly established standards in Michigan. I'm going to show you a little bit later what Michigan did, but they set some standards, and if you're below 50 parts per billion for PFOS, which is this one, we're 15.5, they got 22. You can do unlimited land application of biosolids. And what they did was they made a distinction between residential biosolids and industrial biosolids. So, I think it's really important when we talk about this. We certainly don't want to hide the fact that biosolids has PFOS in it, and it's really sort of at that very low very low residential background levels, sort of the background levels we see in many things in our society. There was a study that was done in Sweden, and it looked at a bunch of different countries and took dust samples from households and added up all the different analytes of PFOS, and the average of all of these samples was about 550 parts per billion. And if you recall from that last one, we were at about, if we add them all up, we're at about 45 parts per billion. So household dust has 10 times the PFOS in it, or the PFAS in it, as our bloom, and there's a direct exposure pathway there, because we're inhaling dust all the time. I do the laundry, and I think I'd like to do a test on laundry dryer lint, because that's probably loaded with PFAS as well. So it's just, I think it's really important to keep these things in perspective and talk about the relative risk of a very small concentration going on to, say, a farmer's field. So in that vein, I put together these are all referenced sources here, but here's bloom at 42. It's our most recent. US blood serum is about 7, so we all have on average about 7 parts per billion of PFAS in our blood. And there's studies showing that school uniforms have 3 times as much as bloom. Why? Because we're creatures of convenience. We want to be able to get the spaghetti stains out of our kids' uniforms, so they're stain resistant. Food has it. This is a different study on dust, but it came up with an average of 523. The Swedish study said 550, so that's quite consistent. A big one is cosmetics. There's a lot of it in it so that it's water resistant. When we're accepting our Oscar and we're crying our eyes out, we don't want our mascara to run, so it's got a lot of PFAS in it, and we apply it right to our face. Organic pasta sauce and ketchup has been found. This was actually a Sierra Club study as well. Were found to have high levels of PFAS. Who knows? It might be from the packaging. I don't really know. And the one that really gets me is food packaging. The national average for food packaging is almost 900,000 parts per billion. And California, everybody just applauded California for setting limits. They set their limits at 100 parts per million. And everybody said, yes, thank you. Finally, somebody did something. But 100 parts per million is 100,000 parts per billion. That's what, 2,400 times higher than what we have in our biosolids that are sitting on a farm field. We really need to all come together and figure out where the risks in our society are. So like, if EPA decides that they're going to ban biosolids so that they can say that they did something, a farmer could, in California, not get biosolids, not put that carbon on the soil, not avoid the use of inorganic fertilizers. But he could take his kids through the drive-through at McDonald's and get a Happy Meal and expose them to 2,500 times higher PFAS. So I think it's really important for us to keep these things in perspective. It's even in rainwater. This is a study that looked at precipitation. It's as high as 5.5 parts per billion. That's almost what we are seeing in the blood, and that's I don't think anybody knows exactly where that's coming from, but my theory is that it's from incinerators and the incineration of plastics, because plastic is loaded with PFAS to make it stronger, and paper. So there have been a couple of areas that have decided to ban biosolids or put a moratorium in place. Maine was the first one. There were a couple of farms up there that had been land applied with paper mill sludge in the 1980s. And one of them it's called Songbird Farm. And when people started to talk about PFAS, the farmers tested their soils and they found these very high elevated levels of PFAS in the soil. And they attributed some, probably rightfully so, some negative health impacts to their cattle, to the soils, and possibly the food grown in the soils, because at those high levels, those really high levels, you can see some uptake from plants. At low levels, we don't see it, but if you spike the material to, up near where it is for food packaging, 100,000 parts per million, you can force it up into a plant. And this is paper, of course. Most food packaging is paper, so this is, it's not unlikely that they were up in that range. And when you look at the soil samples, the levels were high enough that we could back calculate. We don't know what the PFAS levels were in the paper mill sludge because nobody was testing it for it in the 80s. But if you back calculated, it was in that range of 100,000 parts per million. So Maine, for my money, I think that they panicked because the public was outraged over this, and they just sort of painted all biosolids with the same brush, and they set limits that nobody could meet. So they all went out of state or went to the landfills. So, we like what Michigan did. Michigan is making the distinction between the industrially impacted sludges and the municipal biosolids. So the new Michigan standards would not have allowed this industrial paper mill sludge to be land applied. It's really important to separate those risks. Arizona had a situation where there were some wells around Tucson, Arizona, that had some hits from PFAS in early 2020. And somebody looked around and said, well, there's biosolids land applied in the county. It must be the biosolids. And Pima County imposed a moratorium. Now, they didn't ban it, but they said, let's do a moratorium. And of course, the municipality said, well, that, your assessment wasn't terribly scientific. Let's see what is actually happening. So they hired the University of Arizona Water and Environmental Technology Center to do a study, and they collaborated with Pima County to conduct this study. And they found, I'm going to show you a couple things here, but ultimately they showed the results, and based on the data, Pima County rescinded the moratorium so that land application could occur again. This is the study. I don't have a link to it here, but if anybody wants it, I can certainly get a copy to you, or you can just Google it. It's on the internet. So this is some of the data there, and I have next to it the data from Songbird Farm, and this is soil PFAS concentration. So they went out and they looked at farms that had received 5 to 10 years of applications of biosolids from Tucson, 12 to 20 years of application, and then local soils that had never received any biosolids. And you can't see the numbers on here, but you can see that the bars are very, very low. And there was a statistically insignificant difference of PFAS in the soils from these three, even the ones that had never received any biosolids. There's no difference. And if you look at the Songbird Farm soil, that's the soil that had been land applied with the paper mill sludge. So this is the type of thing that we absolutely need to eliminate. And I'm hoping that EPA follows suit with, follows the example that Michigan has set. They've already verbally and in writing endorsed the approach, but they haven't told us exactly what regulations they're going to impose. And if you do this math and you look at the soil levels, the 472 parts per billion or whatever it was in the soil, and you back calculate it to what we think the application rate was of the paper mill sludge would have had about 100,000 parts per billion in it, which is what you see in food containers. So the professor there, Dr. Ian Pepper, yes, his name is Dr. Pepper. He also looked at how it migrates through the soil. So he looked at all these different sites that had PFAS on them, and he dug down into the soil column and measured PFAS at different elevations, at different times and everything. And he found that at about 6 feet deep, we got between 90 and 97% attenuation of the PFAS. So it didn't travel beyond about 6 feet deep. So in Arizona, it did not make it, certainly didn't make it down to the groundwater. Now, I use this as an example of, well, it doesn't move through the soil column, and people say, well, that's Arizona. Arizona soils are very different than soils here, which is true. So we're helping to fund Dr. Pepper again to do this in different soils across the nation. One of which sites is in Virginia at a Virginia Tech Ag Research Station. So we're going to get some data sometime towards the end of the year that will either support this or give us something to refute it. But it's it's not moving through the soil column as far as we know yet, and it is statistically no different than the levels that we find on farms that have not received any biosolids. So this is what Michigan did. They tested all of the wastewater treatment plants in the state, and they tested for PFAS, and they made this distinction between industrially impacted and residential, and they set limits. There's a sort of a screening threshold at 150 parts per billion. If you're above that, you can't land apply at all. If you're between 50 and 150, you can apply with certain reporting requirements. And if you're below 50, you can apply it as if it's any other type of fertilizer. So again, we easily meet the Michigan standards, and our farmers are going to continue to get bloom until we are told otherwise. There's another really interesting thing that I dug up. I found this on the internet, but the EU, European Union, has limits for their food. They do testing of food, and they want to make sure that there's not PFAS in it. And that is, of course, coming in many cases from the packaging and how it's handled. And they chose to focus on 4 individual compounds, PFOS and PFOA, like we do in the States here, but also PFHXS and PFNA. And they add those up. And what their recommendation is that nobody eat more than 4.4 nanograms per kilogram of body weight per week. And then so I added up those for us and got 21.71. And I use myself as an example. I'm a 195-pound man, and it would be safe for me to eat 20,280 nanograms per year of these compounds, which means that I would have to eat over 2 pounds of bloom in order to reach this limit. So that seems very unlikely, but it's, we are, I think, well below what is considered to be safe in Europe as well for food. I'm not suggesting that anybody eat the bloom, though. So, here's where it becomes interesting for us too, because we don't want EPA to impose something, or I don't, that isn't going to solve the problem. Like, they can just say, we're banning biosolids. Look, we did something, but I think we could shoot all the biosolids into space, and we would still have PFAS in our blood, and it wouldn't do anything to reduce it. And in the meantime, we're going to lose all those fantastic benefits. We're going to lose the carbon, we're going to lose the nitrogen. You know, when we send it to farms, we not only do we sequester carbon, but they avoid the use of inorganic fertilizer, ammonium nitrate, which takes an enormous amount of energy to make. So we get a double benefit from a carbon standpoint and a carbon footprint standpoint. And I would hate for EPA to impose something, or Maryland to impose something that wouldn't allow us to bring that benefit to the farmers, because the risk is extremely low. And what happened in Maine and New Hampshire, you know, there's this Concord, New Hampshire was taking their stuff into Maine. They couldn't do it anymore because, again, I think Maine panicked and they set those limits so that nobody could land apply. And in many cases, their costs quadrupled. And I don't want to impose this, not that we wouldn't spend money on this if it was a problem, but the risk is so low. I think that it's unfair of us to impose this on our ratepayers. I think that we really need to look at relative risk, because the exposures with other pathways in their life is much, much higher. So we look forward to, you know, the results of the risk assessment for land applying municipal biosolids. That's going to come out sometime in the next year, I think. We're confident that EPA science will support Dr. Ian Pepper's assessment that there's minimal risk from this valuable and longstanding practice of recycling biosolids. So in the meantime, you know, Bloom is we're going to continue to bring it to farmers so that we can help farmers reduce their dependency on chemical fertilizers, lower our carbon footprint, and ultimately save valuable ratepayer funds. I'm sure there are a million questions, so I think with that, I'll open it up.
Thank you, Chris. I appreciate that.
Sure.
We do have a question that how are drugs or medications measured in wastewater or Bloom?
Yeah, we're required to do priority pollutant testing, and that tests for some of that. You know, PFAS was never included on that, so we started to do it voluntarily. Now some of the states are requiring us to do it, but we've been doing the data. We wanted to understand what the risks were, you know, and if we were doing something that was causing harm to the environment or human health, we would of course do something different. So we got ahead of the regulations and ahead of the regulators and started testing as early as 2018. And there's, you know, lab tests that we send in. There's a suite of tests that we can send our material in and get priority pollutants done.
All right, thanks for that.
Sure.
Can you tell us what it's a bit of a long question in the chat there. The cumulative impact of various sources on our intake, is that taken into consideration in these analysis about the various sources?
I'm sorry. Go ahead and finish.
No, that's it, about the various sources.
Yeah, it's hang on a second. It is typically not done. It's done on an individual basis. I am currently working on a study to look at the cumulative effects, and we're in the first phase of it, really started designing how we would do that. We saw that as a hole in the research that we wanted to fill. So we're working on that, and we're certainly going to share that with EPA when we get some results. But typically, it's done on an individual compound basis. You know what the EU did though, looking at four compounds that they see as prevalent in food, is sort of a start of that, compounding the four different things in the same family of compounds, and then setting a regulation based on that.
I understand. Thank you. So I guess the question is, we're trying to reduce the exposure from all sources, and how is leaf grow gold? Paper mill sludge. Are you seeing this in the chat?
I'm not, I'll pull it up.
The issues that Maine has had with PFAS has been devastating for farmers. It's been from paper and mill sludge, as noted, but we also have sources of soil amendments such as leaf grow, which is made from food waste and carbon waste. So why would we take the risk of adding PFAS to those sources? Is the question.
Yeah, it's just, I don't think there's any great solution for the issue. That's why I sort of talk about the relative risk, that's extremely low levels going onto the soil, as opposed to going to the landfill where it comes back to the treatment plant. It gets concentrated, or ending up at an incinerator that then disperses it into the atmosphere. It doesn't at those extremely low levels that we have, it doesn't get taken up by plants. Ideally, we shouldn't have any PFAS, but none of us thought of that when we were buying these products of convenience. So I think that we have to deal with it, and it's, I think that source control is the solution. We just need to get rid of these products.
Can you explain how bloom compares to milorganite? Is it similar?
Well, similar only in that it is a biosolid product, but milorganite is dried, so it drives off all the water, and it's 90% solids and put in a bag. We use a dewatering system that just squeezes the water out, so it gets to about 32% solids. Now that sounds like it's pretty wet, but it's not. It's just like moist soil. But the source is exactly the same. It's wastewater solids. They just dry theirs further, and they pelletize it.
Thank you. Understood. Well, it looks like that might be the end of all of our questions for today. I want to thank you very much for your presentation, and I want to also thank all of our wonderful tech team and all of you for joining us to hear about all this great soil content and information. I have once again put the feedback form in the chat box if anybody's interested in providing feedback for this presentation. Please visit that link, and we'll also post this conference to the Montgomery County Master Gardener website in the near future. If there's nothing else, happy gardening to you all. Thanks for joining.
Thank you, Ryan.
You're welcome.